what is really on the planet Mars? Today, we head to the red planet, desert-like in appearance, but not as lifeless as it seems. Mars, our intriguing neighbor, still holds traces of a watery past. Dried-up riverbeds, valleys carved by currents, and minerals formed by contact with water. Beneath its frozen surface, salty pockets could still harbor liquid water. And if, in this red dust, lies the memory of a blue world? What if Mars once hosted life, or could still do so? But before embarking on a new adventure, remember to like the video and subscribe to the channel so you don't miss anything. Thank you and bon voyage. When preparing to leave Earth for the planet Mars, the first essential step is to choose the precise moment to ignite the rocket engines, taking advantage of the natural movements of Earth and Mars around the Sun. This favorable period, called the launch window, occurs approximately every 26 months. It corresponds to an optimal alignment between the two planets, ensuring a more energy-efficient trajectory. Indeed, the distance between them varies considerably according to their respective positions, ranging from periods of proximity to much more distant configurations. If this opportunity is missed, one must then wait for the next alignment, more than 2 years later, to regain similar conditions and minimize fuel, time, and resource expenditures. To carry out this interplanetary journey, engineers often choose what is known as a Hohmann transfer orbit. It can be imagined as a vast elliptical arc connecting Earth's orbit to that of Mars, reaching its destination after a controlled travel time. This path is considered the most energy efficient, although it is not the fastest. It would be possible to arrive sooner by greatly increasing thrust, but this would involve massive fuel consumption, making the entire mission more costly and complex. In most cases, this trajectory remains the best option to find a balance between travel time and energy efficiency. However, the travel time can vary from one mission to another. Some robotic probes have taken between 7 and 8 months to cover the distance to Mars. A remarkable example is the Emirates Hope mission, sent by the United Arab Emirates, which reached the red planet in 204 days, setting a speed record in this category. This result was made possible thanks to a rigorous exploitation of the launch window, a perfectly adapted trajectory profile for the spacecraft, and well-controlled maneuvers, avoiding any unnecessary energy expenditure. When no crew is on board, the priority is on the robustness of the probe and the reliability of its instruments. The fuel constraints remain similar. Mass must be optimized to carry the maximum amount of scientific equipment while keeping enough reserve to adjust the trajectory. For a manned mission, the requirements increase significantly. It becomes imperative to bring food, water, oxygen, a functional living space, as well as all the systems necessary for survival. Safety also imposes redundancy of essential devices. Multiple alternatives must exist in case of failure during the journey. These precautions add weight, which increases fuel demand and makes planning even more complex. When the spacecraft carrying the Perseverance rover approaches Mars, the key moment is to insert the probe precisely into the orbit of the red planet. It is not enough to follow a linear trajectory. The probe must integrate stably into the Martian gravitational influence zone, then initiate a rigorous descent. Contrary to the image of a direct landing, reality involves a series of complex maneuvers starting with orbital insertion. At this stage, the speed must be modified so that the elliptical trajectory then guides toward the final approach phase. This process relies on meticulous corrections and appropriate propulsion, intended to counter the planet's attraction while maintaining the energy necessary to reach the targeted area. Once in orbit, ground teams organize the descent sequence with great precision. The goal is to reach a very specific site, the Jezero crater. This ancient lacustrine basin, 45 kilometers, 28 miles in diameter, houses an exceptional fossil delta for research. NASA specialists, particularly at the Jet Propulsion Laboratory, have studied this region using satellite data. They have identified characteristic mineral formations, such as clays and carbonates. These substances are known for their ability to preserve ancient molecular traces. The aim is therefore to detect, in the rock and sediment deposits, ancient biological signatures, or at least chemical markers, of a previously abundant water presence. Before considering landing, a crucial step must be managed: aeropropulsive braking. Although very thin, Mars's atmosphere, primarily composed of carbon dioxide, can be used to slow descent thanks to air resistance, similar to a parachute. For perseverance, this phase begins with a heat shield capable of absorbing the extreme temperatures of re-entry. Then, the upper structure of the module acts like a parachute, but the low air density requires an imposing size and deployment with extreme precision to avoid any failure. Despite this, the parachute alone does not sufficiently reduce the speed for a smooth landing. This is where the so-called aeropropulsive descent comes in. Adjustable thrusters take over and steer the craft by compensating for the thin Martian atmosphere, guiding it towards the target. This steering occurs while the speed remains too high for a secure contact. The device must maintain perfect stability, react to atmospheric variations, and adjust its trajectory in real time. During these critical few seconds, it captures ground images to visually locate itself. A camera compares the observed terrain to integrated maps and identifies, the safest spot for landing. Then comes the moment of the sky crane. This system, introduced during the Curiosity mission, is used here with the same principle. A platform equipped with engines stabilizes a few meters above the ground. While hovering, it deploys cables to lower the rover slowly. This method prevents the thruster jets from disrupting the craft's mechanics upon ground contact. Once the rover is down, the cables automatically detach and the platform moves away to crash at a distance, ensuring the rover's integrity. This spectacular device remains one of the most striking elements of this landing operation. With the rover now installed on a stable base, the choice of the Jezero crater takes on all its importance. Geological studies suggest that several billion years ago, this area hosted a body of water. Orbital analyses have revealed a well-preserved ancient delta, formed at the mouth of a watercourse, identifiable from space. Even today, sedimentary layers arranged in a fan shape, much like terrestrial deltas, can be distinguished. These deposits would have taken time to form, during a period when water flowed on the Martian surface. A deltaic environment, therefore, favors the preservation of possible biological traces, thanks to mineral particles capable of trapping organic compounds and protecting them from alterations. Clays, also known as phyllosilicates, are privileged witnesses of past interactions between rock and liquid water. On Earth, we know that some clay-rich lakes sometimes preserve microfossils or chemical imprints of ancient biological activities. This potential is precisely what led scientists to target the Jezero Delta. There are also carbonates, minerals formed in the presence of dissolved carbon dioxide, also capable of trapping organic elements or essential life components. On our planet, carbonate rocks sometimes contain stromatolites, fossil formations resulting from microbial colonies. Even though Mars does not necessarily present the same structures, this analogy allows us to imagine that ancient life forms could also have left an imprint in the rock. In parallel to the mineralogical data, it should be noted that the Jezero crater presents a topographical interest for landing. The terrain remains moderate, and the surface is not saturated with major obstacles. Despite the presence of edges and rugged areas, engineers have identified several relatively flat zones compatible with precise landing. Its diameter of about 45 kilometers or 28 miles provides an ideal perimeter for exploration. To study an ancient fluvial and lacustrine environment, it is essential to be able to move from the edges of the delta to its center, crossing different strata. Each of these preserves revealing elements about the evolution of water and climate. This crater, whose name comes from a village in the Balkans, was designated as a target site well before the launch. The teams at the Jet Propulsion Laboratory compared numerous locations, weighing their advantages and risks before selecting Jezero as the most suitable for the primary objective, the search for potential biosignatures. Data transmitted by orbiters such as Mars Reconnaissance Orbiter have made it possible to establish detailed spectral maps of the soil. Thanks to the analysis of the light reflected by the surface, the onboard instruments have revealed the presence of clays, carbonates, and other mineral formations associated with wet environments. Beyond the mere quest for biological traces, Jezero allows for the reconstruction of a large-scale geological sequence. By exploring the terraces and deposits left by an ancient river, it becomes possible to draft a relative chronology of major upheavals, such as volcanic eruptions, climatic changes, or fluctuations in the magnetic field. Even without direct proof of past life, the analysis of this region would offer essential insights into ancient conditions, particularly the atmospheric evolution. Understanding the gradual disappearance of liquid water on the surface remains a central question in studying Mars's fate. During the planning of the descent to the delta, teams know they must aim with an extremely narrow margin of error. On the scale of an entire planet, reaching a target just a few dozen kilometers wide represents a considerable technical challenge. This level of precision relies on onboard systems capable of recognizing the terrain in real time, comparing their sensors' data to the maps stored in the onboard computer. This guidance capability is what distinguishes a successful landing from a failure. But the timing window also counts. The mission must avoid periods of strong dust storms, which compromise visibility and stability. One of the fundamental reasons that led NASA to focus its efforts on Jezero lies in the unique configuration of the delta. This location allows for observing, in a single area, several major stages of Martian hydrologic history. First, there are the lower layers, witnesses of the earliest deposits. Then, moving upward, more recent strata tracing the basin's evolution. By reaching the boundary between the delta and the crater's slopes, Perseverance can collect samples representative of a wide geological variety: clays, carbonates, volcanic rocks transported by the waters, or fragments from ancient impacts. All these samples are sealed in specially designed metallic tubes for a potential return to Earth for detailed laboratory analysis. Thus, the orbiting around Mars and the choice of a site like Jezero answer to a rigorous logic, both technical and scientific. Without perfect mastery of the descent and contact point, any hope of discovering evidence of life would have been compromised. Thanks to the aero-propulsive braking and the ingenious sky crane device, the rover was able to safely reach a terrain of major geological interest. It is there, at the heart of the sediments of an ancient lake, that it begins one of the most in-depth explorations ever conducted on Mars. The clays and carbonates act as chemical archives, which researchers hope to decipher to reveal traces of biological activity or, at the very least, construct a solid narrative of the planet's climatic history. Remotely, the Jet Propulsion Laboratory monitors every movement, rigorously collecting the information sent by the device. What makes Jezero so captivating is this rare combination of the promises of a watery past and the possibility of understanding why Mars lost its lakes and rivers. This site, chosen from a multitude of options, almost single-handedly embodies the expectations of an entire scientific community, discovering if Mars could have ever hosted life. Its delta, frozen in the rock, might just be the key. If microbial forms once thrived in these ancient waters, it's possible they left tiny imprints in the minerals, chemical traces preserved in the material. Today, Perseverance, equipped with an arsenal of powerful instruments, is tasked with probing these strata. High-resolution imaging, spectrometry, laser analysis, each tool contributing to a meticulous quest. This is the culmination of many years of preparation, calculations, scientific debates, and above all, a collective genius capable of pushing the boundaries of space exploration. This is why the trajectory towards Jezero and the selection of its site are of paramount importance. They constitute the starting point of an investigation aimed at unveiling the history of life in the solar system. Each step depends on the previous one: orbital insertion, atmospheric braking, powered descent, activation of the sky crane, and then targeted exploration. This rigorously orchestrated technological sequence pursues a single goal: to collect reliable clues that could revolutionize our understanding of the universe and our place among the stars. Ultimately, if Perseverance managed to land there, it's thanks to the precision of orbital guidance, the mastery of braking, and the intelligence of the landing system. And if Jezero was chosen, it's because its rocks might still whisper what water was on Mars, and maybe what life was like there. When flying over Mars for the first time, the dominant sensation is of a world both close to Earth and strangely different. The red planet, whose hue comes from the abundance of iron oxide in the soil, reveals monumental landscapes shaped by geological processes acting over billions of years. To grasp the magnitude of this terrain, one must envision vast volcanic plateaus, breathtaking canyons, and ice caps covering the poles, all enveloped by a thin atmosphere dominated by carbon dioxide. To fully immerse yourself in this universe, I propose a visual and analytical journey, highlighting the major features of the terrain, the characteristics of the atmosphere, and the effects of the disappearance of the global magnetic field. Let's begin with the Tharsis Massif, considered one of the most imposing elements on the Martian surface. This gigantic bulge of the crust spans several thousand square kilometers or miles. It houses volcanoes of colossal size, among the most impressive in the solar system. Notably, it includes Mount Olympus, or Olympus Mons, often cited as the tallest shield volcano ever observed. It rises nearly 22 kilometers, or 14 miles, above the surrounding plains, more than twice the height of Everest. A shield volcano is characterized by its gentle slopes, formed by fluid lava spreading over long distances. On Mars, this spectacular morphology is partly explained by the lower gravity, about a third of that on Earth. The rigidity of the Martian crust has also allowed these structures to grow over long periods without collapsing. These volcanoes testify to a prolonged volcanic activity that has greatly shaped the terrain, particularly during the planet's more geologically active eras. Leaving the highlands, the eye is irresistibly drawn to another major structure, Valles Marineris. This canyon system tears across the surface for thousands of kilometers or miles. Its length far exceeds that of any terrestrial canyon. At certain points, it reaches nearly 8 kilometers or 5 miles deep and several hundred kilometers or miles wide. Its formation originated from crustal fractures caused by the rise of Tharsis. Imagine colossal tensions deforming the surface until monumental collapses occurred. Subsequently, Erosion processes such as landslides or intermittent water flows have modified and amplified its walls. Today, Valle Marineris offers a window into the geological depths of Mars, where exposed strata reveal traces of ancient volcanic activity, sedimentation, and tectonic movements. After traversing Tharsis and crossing Valles Marineris, the journey continues towards the poles. There, one discovers the ice caps, present both in the north and south, which vary in extent with the seasons. Composed mainly of water ice, they also contain a portion of solid carbon dioxide that forms or sublimates according to temperature variations. In winter, the cold is such that the atmospheric carbon dioxide deposits directly onto the ground as dry ice, temporarily increasing the size of the ice cap. In spring, with the return of milder temperatures, this ice transforms into gas and rejoins the atmosphere, causing the polar cover to recede. This cycle has no equivalent on Earth, where carbon dioxide does not naturally condense at the surface. On Mars, this seasonal phenomenon plays a central role, as it directly affects the atmospheric pressure, with a significant fraction of the atmosphere depositing on the ground before evaporating again. To understand what characterizes the Martian atmosphere, one must first recall its extreme thinness compared to Earth's. The average surface pressure is about 6 millibars or 0.09 psi, compared to over 1,000 or 14.7 psi on our planet. This means the Martian air is less dense than that of Earth by significant proportions, although it is mostly composed of carbon dioxide with some traces of nitrogen and argon. At this pressure, liquid water cannot subsist sustainably. It freezes or evaporates almost instantly. This thin atmosphere accentuates thermal variations. The temperature differences between day and night can be extreme. Temperatures drop below minus 100 degrees Celsius or minus 148 degrees Fahrenheit at the poles in winter and can, under very specific conditions, reach about 30 degrees or 86 degrees Fahrenheit at the equator in summer. This phenomenon can be explained by the fact that the heat accumulated during the day escapes quickly due to a lack of sufficiently dense air to retain it. Like Earth, Mars experiences a seasonal cycle, but each season lasts almost twice as long. The Martian year extends over about 670 Earth days. Furthermore, its orbit is noticeably elliptical. This shape causes a significant variation in distance from the Sun depending on the position on the orbit, influencing the amount of energy received. Thus, the seasons are not perfectly symmetrical. In the southern hemisphere, for example, summer is shorter and more intense, while winter extends further, accompanied by lower temperatures. One of the most spectacular atmospheric phenomena is that of dust storms. On Mars, winds can lift fine iron-rich particles, forming impressive whirlwinds. Unlike on Earth, where such events remain localized, these storms can extend planet-wide. Some envelop the entire surface under a reddish veil for several weeks, blocking sunlight. The trigger mechanism for these global storms remains poorly understood, although they often occur at the transition to spring or summer in the southern hemisphere, where thermal contrasts are most marked. The suspended dust warms the atmosphere, altering its dynamics, which in turn fuels new winds. These storms affect both visibility, the proper functioning of solar machines, and the planet's temporary climatic conditions. If Mars today presents such an extreme climate, it is partly because it has lost a fundamental protective element, a global magnetic field. Unlike Earth, whose liquid core generates a powerful shield, Mars no longer has one. In a distant past, such a magnetic field likely existed, but extinguished billions of years ago. Since then, the solar wind strikes the upper atmosphere without a real barrier, contributing to its gradual erosion. In the absence of protection, the Martian surface is also subject to intense radiation. For future explorers, this implies strict protective measures, special suits, underground shelters, or using natural structures like caves. These radiations also pose a problem for the preservation of organic molecules, which can deteriorate rapidly upon contact with this radiation, especially in exposed soil layers. Let's imagine a scientist on Mars, protected by an insulating suit, moving across a reddish ground littered with rocks and craters. On the horizon, plateaus marked by channels suggest ancient lava flows from the Tharsis Plateau. Further away, the contours of a canyon might reveal the tip of Valles Marineris. In the pale daytime sky, or tinged pink at dusk, a light dust cloud sometimes floats. In certain seasons, this veil becomes a dense haze, gradually obscuring the landscape and plunging the environment into a lasting ochre light. Without a global magnetic field, the surface remains exposed. The light diminishes, making life difficult for any form of biology or solar equipment. This world, harsh yet fascinating, continues to captivate those interested in planetary geology and extraterrestrial environments. The general portrait of Mars rests on key structures: the vast volcanic plateau of Tharsis, the giant rift of Valles Marineris, the icy poles where water and carbon dioxide alternate with the seasons, a thin atmosphere capable of triggering immense storms, and the absence of magnetic protection. Each element is connected to the others. Volcanism has shaped the heights. Tectonics have carved the chasms. The ice caps record seasonal cycles, and the atmosphere, subjected to the solar wind, continues its evolution. By observing these interactions, one can understand the complex history of this planet, whose transformation is slowly ongoing. Its seasons shape the poles, its storms redistribute the dust, and its relief reinvents itself under the effect of time. At the beginning of Mars's geological history, long before icy winds and dust storms shaped its desert landscape, the planet offered a radically different setting from what we observe today. Researchers name its earliest period the Noachian, an era that is estimated to extend between about 4.1 billion and 3.7 billion years ago. At that time, Mars had a much warmer and wetter climate than it does now. Data collected by orbiters and rovers suggest the presence of liquid water on the surface through a multitude of geological clues. To grasp the extent of this transformation, one must explore the valleys carved by erosion and the deposits of minerals altered by water. The valley networks, these branched incisions that crisscross the Martian ground, are among the most important witnesses to the ancient action of water. During the Noachian, heavy rainfall or prolonged runoff might have shaped the surface, carving riverbeds that stretch sometimes over considerable distances. These structures, now dried up, are revealed through observation from orbit. By analyzing their morphology and the organization of sediments, geologists highlight a hydrological dynamic that profoundly sculpted the landscape. The formation of such networks implies the existence of a water cycle comparable to that of our planet, including evaporation, condensation, and rain. This hypothesis is reinforced by the presence of mineral deposits formed by the prolonged action of water. Among the most significant mineralogical clues are phyllosilicates, a category of minerals resulting from prolonged interaction between water and silicon-rich components. On Earth, these substances appear in various contexts, notably in clays resulting from the decomposition of volcanic rocks. On Mars, their detection indicates a sustained circulation of water, capable of altering the chemistry of rocks over long periods. Their presence in terrains dating from the Noachian suggests that this wet phase extended across the planet and lasted several 100 million years, a duration sufficient to offer an environment conducive to the emergence of habitable conditions. Beyond the valleys and minerals, a broader hypothesis has emerged: the existence of an ocean covering the northern hemisphere, which researchers refer to as the Boreal Ocean. According to several studies, towards the end of the Noachian period, about 3.7 billion years ago, the lower topography of northern Mars would have allowed the accumulation of a vast body of water. The analysis of reliefs, possible shorelines, and certain sediments fuels this hypothesis. If this ocean did indeed exist, it would have constituted a massive reservoir of liquid water, capable of maintaining a more temperate climate and a denser atmosphere, at least for a significant period in Martian history. But this theory is not unanimous. One of the great challenges remains to determine the fate of all this water. Today, Mars is dry, subject to very low atmospheric pressure, with temperatures ranging between -60 degrees Celsius or -76 degrees Fahrenheit and a few degrees above zero in the equatorial regions in summer. Much of this water would have dissipated into space following the disappearance of the global magnetic field, or could still be present as ice in the polar caps or buried in the subsurface. Researchers rely on the analysis of hydrogen isotope ratios to estimate the amount of water lost and that which still exists beneath the surface or as frozen forms. The chronology of this aquatic presence is refined through on-ground and orbital analyses. The studies of rock alteration, notably via spectrometers on board satellites, show that phyllosilicates are concentrated in the oldest terrains. After the Noachian, Mars enters the Hesperian period, an era marked by extensive volcanism and the appearance of large lava plains. During this period, surface water declines significantly, although isolated episodes might have allowed for a temporary return of liquid water. The gullies observed on the walls of certain craters could thus result from the sporadic melting of underground ice or the uprising of saline fluids. The hydrological history of Mars does not, therefore, stop at the Noachian, but is part of a long and complex evolution. The possibility that a true ocean covered a significant part of the planet in the Noachian or shortly after continues to stir debate. Proponents of this hypothesis rely on structures evoking ancient shorelines and on the nature of certain sediments similar to those observed in coastal areas. Altimetric data collected by space probes suggest that the Boreal Basin could have contained enough water to cover nearly a third of the planet. Other scientists propose alternative explanations. These landforms could result from tectonic processes or collapses unrelated to an ancient ocean. Recent geochemical measurements, particularly isotopic analyses of the Martian crust, introduce new variables, sometimes contradictory, depending on the envisaged models of atmospheric loss and climate transformation. Despite these uncertainties, the study of Martian water reveals a past much more active than the current surface suggests. To date, one certainty remains. Water truly flowed on Mars during the Noachian in the form of rivers, lakes, and possibly a partial ocean. The vast valleys, sedimentary layers, and hydrated minerals, especially phyllosilicates, constitute the most eloquent traces of this wet era. Together, they suggest that Mars might have met the necessary conditions for the emergence of microbial life. Understanding the reasons for this gradual loss of water, while Earth managed to preserve it, equates to exploring the deep mechanisms guiding the evolution of terrestrial worlds. Every new piece of data, every isotopic analysis, every orbital image, thus helps illuminate a bit more the shadowy areas of this complex Martian past. Welcome to Jezero Crater, a vast depression, 45 kilometers, 28 miles in diameter, carved into the arid lands of Mars. We are at the fifth stage of our exploration, dedicated to studying a remarkable ring of carbonates discovered in this region and its potential for revealing possible traces of ancient life. To fully grasp the significance of this discovery, we should revisit the nature of these minerals, the conditions of their formation in a lacustrine environment, and their ability to enclose biological clues. We will also examine a sample named Comet Geyser, collected by the Perseverance rover, and establish a connection with terrestrial formations known as stromatolites, mineralized remnants of ancient microbial communities. Before detailing the characteristics of this carbonate ring, let's explore the definition of this type of mineral. Carbonates generally form when dissolved carbon dioxide reacts with elements like calcium or magnesium, resulting in solid precipitates. On Earth, calcium carbonate is a common example, found in limestone or marine organism shells. On Mars, a similar mechanism could have occurred if, in the past, water and carbon dioxide were abundant, either in the atmosphere or on the surface. The presence of carbonates in a ring in Jezero suggests that a body of water might have occupied this area billions of years ago. This circular formation visible on the periphery of the delta is referred to as a carbonate ring. According to scientists, it would correspond to an ancient shoreline or a lakeshore. In such an environment, carbonates play an essential role in regulating the acidity level of the water, maintaining a chemical balance conducive to the stability of organic compounds. This pH consistency is crucial as it conditions the preservation of potential biosignatures. A rapid fluctuation of the chemical environment would compromise the preservation of biological structures. Thus, carbonates are prime targets for detecting ancient markers of life. In February 2021, the Perseverance rover landed in Jezero to explore signs of past microbial activity. Among the samples studied is Comet Geyser, taken precisely from the area where the carbonate ring extends. This sample has been subjected to detailed analyses thanks to the onboard instruments. What makes it particularly interesting is the ability of carbonates to enclose microscopic inclusions, sometimes rich in organic matter. On our planet, these inclusions often reveal residues of ancient cells. If a similar phenomenon occurred on Mars, Comet Geyser could hold crucial information about a vanished life. To understand how these minerals trap biological traces, we must examine the chemical process leading to their formation. When lake water is saturated in carbon dioxide, reactions occur with cations like calcium or magnesium, causing the precipitation of carbonates. This mechanism, although slow, generates successive mineral strata. As these layers are deposited, they trap suspended elements, microorganisms, organic debris, or mineral particles. When the water evaporates or retreats, these deposits solidify, preserving the elements they captured within. This principle makes terrestrial carbonates so valuable to researchers. Some ancient limestone massifs contain stromatolites, considered the oldest evidence of life on Earth. These structures appear when colonies of cyanobacteria locally promote the formation of carbonates, producing over time superimposed mineral laminae. These formations, dome or column-shaped, become geological archives revealing primitive biological activity. The presence of carbonates around Jezero Delta suggests a similar process may have occurred on Mars. Although the exact nature of any potential life forms remains unknown, past environmental conditions seem to have been more hospitable. The lake that occupied this crater received water through ancient valleys, depositing mineral-rich sediments. When the climate changed, the body of water receded, leaving behind these carbonate deposits in a ring shape, still visible today. If microbial life existed, it could have left traces buried in the rock. The Perseverance mission thus dedicates a significant portion of its analyses to these formations. The rover's instruments, capable of identifying the chemical signature of minerals, allow the precise study of carbonate composition and determine if they contain organic substances. In the case of Comet Geyser, the initial data reveals a mineral association that could favor the preservation of complex compounds. Even if no formal evidence has yet been identified, these findings strengthen the hypothesis of ancient habitability. To go further, researchers are also analyzing the internal structure of Comet Geyser. On Earth, the presence of stromatolites can be recognized by laminated patterns alternating between organic and mineral matter. If such organization is detected in Martian carbonates, it would be a major discovery. However, the instruments of a rover have their limitations. Only analyses conducted on Earth, with more sensitive equipment, will determine if these structures have a biological origin or not. This is why the carbonate ring of Jezero, in connection with the Comet Geyser sample, constitutes one of the most promising clues in the search for past life on Mars. These mineral formations could very well be the silent witnesses of an ancient world where chemistry, water, and life might once have coexisted. When one mentions Mars, the image of an arid and silent desert immediately comes to mind. Yet, amidst this apparent austerity, the Curiosity rover, having arrived in Gale Crater, has highlighted unexpected and captivating clues. These elements present themselves as organic compounds, primarily consisting of carbon and hydrogen, sometimes linked with other atoms like oxygen, nitrogen, or sulfur. A central question then emerged. What is the exact nature of these substances, and how can their presence be explained, whether of geological origin or potentially linked to a biological past? To grasp the scope, one must explore the secrets of Martian chemistry and see how the Curiosity mission has changed our perception of the red planet, before Perseverance enriches this investigation with its own data. From the very beginning, researchers involved in Curiosity did not expect spectacular results. Gale Crater, which is 150 kilometers or 93 miles wide, houses a towering mountain, Mount Sharp or Aeolus Mons, according to the official nomenclature, rising more than 5 kilometers or 3 miles high. This region was chosen for its stacked rock layers, true geological archives of the planet. Once in place, Curiosity used a range of tools to drill into these strata and extract their composition. It is in these samples that the rover identified organic compounds such as thiophanes, benzene, and toluene. Thiophanes have a ring structure composed of 4 carbon atoms and 1 sulfur atom. On Earth, they are found in certain carbonaceous rocks, crude oils, or even from living processes. Benzene, on the other hand, is a ring of 6 carbons, each bonded to a hydrogen atom, a simple yet essential molecule in the terrestrial chemical industry despite its toxicity. Toluene, finally, corresponds to a benzene ring with an added methyl group formed of 1 carbon and 3 hydrogens. Together, these molecules testify to an unexpected organic diversity on Mars. But the true breakthrough occurred in 2025, when more advanced analyses revealed carbon chains exceeding 10 atoms. These macromolecules indicate structures far more complex than the previous simple rings. Never before had such forms been confirmed on Mars. The Jet Propulsion Laboratory, which oversees the Curiosity data, relayed this discovery. The presence of these long chains suggests sufficient chemical stability in the Martian soil to preserve potentially ancient assemblies, stemming from an environment that, in the distant past, might have been more humid or temperate. When faced with such molecules, a fundamental question arises. What is their origin? On Earth, compounds of this type often originate from biological activities, such as the decomposition of organic matter or the action of microorganisms in sulfur-rich environments. However, abiotic mechanisms can also produce these substances. Chemical reactions in rocks or the delivery of celestial bodies like comets or meteorites can sometimes suffice to generate them. The results obtained from drilling do not yet allow us to identify the exact pathway, but they indicate that Mars preserves traces of ancient chemical processes. Deciphering these clues is akin to tracing back the timeline in search of conditions that might have made the planet habitable. While Curiosity multiplied its analyses, Perseverance began its own exploration. This rover is equipped with a specialized device, the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, or SHERLOC. Unlike its predecessor's drilling tools, this instrument uses an ultraviolet beam to examine surface rocks. When organic compounds are exposed to this light, they can emit fluorescence, a characteristic glow that helps identify aromatic structures, such as those observed in benzene or toluene. The first observations by Perseverance showed that the J0 crater also contains aromatic compounds. But quickly, a scientific controversy emerged regarding the interpretation of these fluorescences. Indeed, while they reveal the presence of organic molecules, they do not allow us to distinguish between a mineral origin, an external source, or an endogenous chemistry that might have involved microorganisms. This uncertainty calls for extreme caution. The study of Mars is built step by step, distinguishing purely physical processes from those that might pertain to living organisms. In this context, the issue of perchlorates is crucial. These compounds, made up of a chlorine atom surrounded by 4 oxygens, are powerful oxidants. Their widespread presence, confirmed by probes like Phoenix, profoundly alters our understanding of the Martian soil. On one hand, they lower the freezing point of water, making the existence of brines possible. On the other, they rapidly degrade organic compounds. Yet, despite this chemical aggressiveness, Curiosity and Perseverance have identified the persistence of thiophenes, aromatic cycles, and even macromolecules. These results suggest the existence of more protected reservoirs capable of preserving chemical signatures in hostile conditions. A crucial issue remains, ensuring the absence of terrestrial contamination. The detection of organic molecules would only be significant if it is certain that they do not originate from equipment sent from Earth. For this reason, each interplanetary mission follows rigorous sterilization protocols. Despite these precautions, a minute doubt always persists. This is why detected signatures are systematically compared with those recorded on Earth before launch to identify their true origin. To date, Curiosity has examined hundreds of samples in Gale Crater. Perseverance, on its part, continues its research in Jezero. Although their objective is not to directly demonstrate the existence of Martian life, the elements they collect are crucial pieces. The presence of aromatic rings and complex chains in an oxidizing environment, exposed for billions of years to solar radiation due to a thin atmosphere, surprises researchers. It suggests that certain areas of Mars have managed to preserve ancient chemical clues buried in rocks or protected within fissures. Many uncertainties remain. How did these structures evolve before being encapsulated in rock? What influence did radiation have on their initial form? Are there richer deposits buried deeper, sheltered from destructive agents? These questions currently drive planetary research. A more precise answer could emerge from the study of Martian samples returned to Earth. Advanced laboratories could then analyze their details. This scenario is envisioned as part of a future joint mission between NASA and the European Space Agency. For now, the collected data reveal a more extensive and resilient organic chemistry than expected. In summary, the clear identification of compounds ranging from simple structures to very elaborate macromolecules marks a turning point. Thanks to Curiosity's drilling tools and Perseverance's light detection, an organic inventory has been drawn up. While these findings alone do not prove the existence of life, they demonstrate that some fundamental components are indeed present in the oldest areas. A precise distinction between natural and biological origins could one day profoundly change our understanding of life in the universe. To progress, we must continue to drill, probe new types of regolith, and explore less exposed areas. A large part of Mars remains unknown. Every new piece of data, every detected chemical signal, every light trace revealed by the instruments adds a fragment to this still under construction narrative. Despite the action of perchlorates, some markers have survived. Curiosity has helped us reach a milestone by demonstrating the complexity of Martian soil, and Perseverance refines this vision with targeted analysis methods. We advance slowly, gradually unveiling the contours of a once unsuspected world. What these missions have already uncovered exceeds expectations and foreshadows future major revelations. In this search for origins, we better understand the importance of these molecules. Thiophanes, benzene, toluene, all fundamental building blocks that suggest the existence of environments conducive to prebiotic, even biological processes. The discovery of macromolecules extends this hypothesis. Mars could have, in the distant past, offered a much richer environment than previously imagined. It remains to precisely analyze the structure, isotopes, and geological context of these compounds to exclude other explanations, such as a meteoritic or mineral origin. In this regard, terrestrial laboratories are developing new methods to study these substances remotely or to preserve intact those that might one day be brought back. The ultimate goal is clear: to identify indisputable signatures. Such an outcome would revolutionize our perception of life in the universe and make Mars a credible candidate for harboring ancient biological phenomena. Meanwhile, every new detection, every spectrum measured, every interaction analyzed brings us closer to this threshold. The Martian narrative is still being written, and these organic molecules occupy one of the most promising chapters. When we explore the noble gases present in the Martian atmosphere, we enter a fascinating dimension of planetary study. Imagine yourself aboard a spacecraft orbiting Mars, carefully observing the instruments that analyze this thin veil of air. This is where our journey into the research on methane and hydrochloric acid begins, two compounds that raise many questions in the scientific world. To grasp the stakes, we must go back to the origins of this research. For years, the possibility of methane presence on Mars has intrigued researchers. This molecule is often associated with biological mechanisms on Earth, but it can also result from geological activities. Here, methane mostly comes from microorganisms, like methanogenic bacteria. However, non-living processes can also produce it, notably by the alteration of certain minerals exposed to heat, or during reactions involving iron-rich rocks in contact with very hot water. Thus, detecting methane on Mars raises an essential question. Could it be evidence of ancient or current life, or is it the result of a purely mineral phenomenon? This mystery has fueled debates for several years. Let's start with the most striking element of this investigation: the readings taken by the Curiosity rover, sent by NASA and arrived in Gale Crater in 2012. Equipped with extremely sensitive instruments, it can detect tiny traces of gas in the Martian air. Programmed to regularly analyze the atmosphere, it uses advanced spectrometry techniques to separate and identify the molecules present. Gradually, the analyses have revealed recurrent methane spikes in the rover's immediate environment. The observed concentrations reached a few parts per billion by volume. This means that, for a billion volumes of air, only a few methane elements were present. Although modest in appearance, these levels far exceeded the threshold beyond which nothing would be detected. Curiosity observed several sudden methane spikes, sometimes limited to just a few days or weeks, before levels drop back to nearly undetectable amounts. This sudden variability suggests a discontinuous emission, the temporary release of underground pockets, or a yet unexplained seasonal production. With each detection, excitement grew. Researchers were already considering the possibility of a biological origin. But on Mars, rigor is essential. It is established that certain geological reactions are sufficient to explain the presence of methane. Therefore, it was necessary to go beyond simple detection. Validation had to be done independently to attempt to understand the source of this gas. This is where the trace gas orbiter comes into play, developed by the European Space Agency and its Russian counterpart. Having arrived in the vicinity of Mars in 2016, its main mission is to analyze gases present in the atmosphere with extreme precision, even in very low quantities. To achieve this, it is equipped with spectrometers capable of measuring concentrations as low as a fraction of a part per billion. The objective was clear: to confirm or refute the observations made by Curiosity. However, to everyone's surprise, the orbiter detected almost no methane. Despite repeated observations, both near the ground and at altitude, signals remained very weak. The readings indicated concentrations much lower than those recorded on the ground, or even a complete absence. Such a discrepancy naturally triggered a controversy. How can Curiosity detect occasional spikes, while an orbiter, supposedly more efficient, does not detect any? Several avenues have been explored to try to resolve this paradox. One of them is based on the fundamental difference between measurements taken on site and those made from orbit. If the methane is emitted by localized sources or over short periods, the orbiter might easily miss them, simply by not being at the right place or time. Other factors, such as Martian winds and seasonal variations, also influence the dispersion of the gas. It is also possible that the molecules quickly escape into space. Additionally, the detection method used by the trace gas orbiter relies on analyzing sunlight filtered through the atmosphere, which heavily depends on the orbiter's position and the angle of observation. This combination of factors could explain the absence of orbital detection, despite the recordings made on the ground. But this divergence is not only based on the instruments, it also concerns the interpretation of the data. In science, even the slightest difference pushes for improved protocols, confronting approaches, and designing new tools. For now, it is established that Curiosity indeed recorded methane at times, while the orbital probe finds hardly any. The question remains, can brief emissions near the ground elude analysis from space? Investigations are ongoing, and future missions will likely clarify this uncertainty. Let's now turn our attention to another component, hydrochloric acid, an acid composed of hydrogen and chlorine. On Earth, it is well known, both for its role in our digestion and its industrial uses. The idea of finding it on Mars may seem unexpected. However, the Trace Gas Orbiter detected signs of its seasonal presence in 2020 or 2021, according to scientific publications. As with methane, this discovery sparked keen interest. On our planet, hydrochloric acid is rare in the air. Its detection, even sporadic in the Martian atmosphere, raises new questions. Researchers are considering a mechanism based on the interaction between Martian dust and formations of ice or frost in cold weather. Mars often experiences massive dust storms, sometimes covering its entire surface. This dust, rich in chlorinated minerals, could release hydrochloric acid when it comes into contact with water vapor or icy deposits, especially during seasonal changes. It would be a non-biological process. In periods of warming or during sublimation of the ice, these minerals could react and release some gas into the air. The complexity of Martian chemistry, influenced by the nature of the soil, variable temperatures, sunlight, and fluctuating pressures, still leaves many areas unexplored. This recent detection reminds us that despite its extreme thinness, the Martian atmosphere certainly contains several unknown gases, subject to cycles we still poorly understand. Scientists increasingly suspect a correlation between these gases and cycles related to water ice, frozen carbon dioxide, and dust activity. By analyzing their distribution according to the seasons, we gain insights into the nature of the processes at play, whether purely chemical or revealing something else. Since we started addressing the question of methane, a central question arises. Could these gases betray a form of life? On Earth, certain microorganisms produce methane as a byproduct of their metabolism. For a similar phenomenon to exist on Mars, we would have to imagine the existence of bacteria buried beneath the surface, in pockets sheltered from drought and radiation. Some researchers have even suggested Martian perchlorates, these oxidizing salts, as a potential energy source for microscopic life forms. This scenario would imply methane production of biological origin. For now, no formal evidence supports this hypothesis. The debate between geological cause and living origin remains open. Thus, observations of variable methane and the seasonal appearance of hydrochloric acid bring new pieces to the study of Martian atmospheric chemistry. By confronting them with geological data, ancient lakes, fluvial networks, and saline deposits, scientists paint a complex picture. Each advance raises new questions. Are methane emissions solely of mineral origin? Could hydrochloric acid be just a product of interactions between dust and frost? And what if methane transforms into other compounds before reaching the orbital sensors? This aspect of Martian exploration highlights how this planet, seemingly inert, is animated by subtle chemical dynamics. Technologies are improving, spacecraft are multiplying measurements, and mission after mission, our understanding progresses. The next challenge will be to confront the anomalies identified with more in-depth analyses. Future missions aim to bring Martian samples back to Earth to conduct laboratory studies. We will then be able to determine the exact composition of gases, the nature of associated minerals, and the distribution of isotopes, these atomic forms, revealing a possible biological process. In 2022, the Martian rover Curiosity, equipped with a set of scientific instruments called Sample Analysis at Mars, delivered intriguing measurements regarding the proportion of a particular carbon isotope, known as carbon-12. In science, the study of the relative abundance of carbon isotopes helps identify the processes that may have influenced or transformed the organic matter present on Mars. On Earth, these isotopic analyses serve to study fossils, reconstruct ancient environments, and detect traces of past biological activities. For Mars, The sample analysis at Mars instrument revealed unexpected results in 7 different samples, showing particularly low values of the ratio between carbon-13 and carbon-12. Generally, a marked decrease in carbon-13, accompanied by a relative enrichment in carbon-12, opens the door to several interpretations, some of which suggest the possible existence of ancient Martian life forms. To understand the nature of these results, it is essential to define what carbon isotopes are. Carbon is a fundamental chemical element for life as we know it. Organic molecules, like proteins or nucleic acids, are based on a carbon framework. Carbon exists in several forms called isotopes, which differ by their number of neutrons. Carbon-12, the most common, has 6 protons and 6 neutrons. Carbon-13, rarer, includes an additional neutron. On Earth, the proportion of carbon-12 is higher than that of carbon-13, and this distribution changes even more under the influence of biological processes. Indeed, during photosynthesis or other metabolisms, living organisms preferentially incorporate carbon-12, leaving a distinctive signature in fossil tissues or ancient sediments. When discussing the ratio of carbon-13 to carbon-12, we compare the value measured in a sample to a terrestrial standard. A very low value of this ratio indicates that carbon-12 dominates over carbon-13 compared to the usual average. On Earth, this isotopic signature can result from the degradation of organic matter, microbial production, or photosynthetic activity. Thus, when the sample analysis at Mars instrument detected a very low carbon-13 ratio in 7 Martian samples, the main question was, what explanations could justify this result? The first hypothesis involves ultraviolet photolysis, a process where solar ultraviolet rays break down certain molecules. Mars's atmosphere, much thinner than Earth's, exposes the surface to intense solar radiation. This photolysis could fragment carbon molecules in the atmosphere or on the surface, increasing the proportion of carbon-12 in the measured residues. According to this scenario, ultraviolet radiation could have, over long geological periods, preferentially removed carbon-13, making it rarer in the remaining sediments. However, this hypothesis requires a better understanding of the deposition mechanisms of these products on the Martian regolith, as well as the actual impact of photolysis on the observed isotopic signature. A second hypothesis suggests an external input of organic molecules or carbon compounds from celestial objects, like comets. These bodies, rich in ices and complex organic molecules, can, during impacts or micrometeorite showers, leave a peculiar isotopic imprint. Researchers then compare the carbon-13 and carbon-12 signatures of these debris with those of the 7 samples. If the match is strong, it would indicate that the Martian anomaly comes from meteoritic or cometary events. However, for the proportion of carbon-12 to be so high, a series of carbon-rich impacts over a long period would be necessary, which remains difficult to establish. The third hypothesis, the most captivating, concerns possible ancient microbial activity. On Earth, certain microorganisms derive their energy from reactions involving carbon. They prefer to capture carbon-12, which is easier to integrate into their biochemical processes. This selectivity can leave a higher concentration of carbon-12 in the sediments, used as an indicator of past life in terrestrial rocks. The fact that Curiosity detected 7 samples with a very low carbon-13 ratio strengthens the idea that microorganisms might have once thrived on Mars in a wet and chemically favorable environment. Yet, demonstrating a biological link remains a major challenge, given the current absence of a biosphere and the complex Martian geology. It's not enough to observe this isotopic imbalance. One must understand the burial processes, local variations, and transformations since that time. To delve deeper into this lead, scientists seek to cross-reference multiple clues. They examine if other substances, like complex organic molecules or specific minerals, are systematically associated with these isotopic anomalies. On Earth, particular sulfur deposits or sedimentary structures like stromatolites often testify to ancient life. On Mars, robotic exploration attempts to find equivalents. The Curiosity rover, followed by Perseverance in another crater, places these findings in a broader geological context. Which rocks carry these signatures? To what periods do they date back? Do these rocks present structures compatible with an ancient lake environment, favorable to life? All these questions intertwine and require years of detailed analyses, but the results from the sample analysis at Mars Instrument stimulate the quest for an answer to this mystery. It is also necessary to place the measure of this carbon-12 enrichment within a methodological framework. The instrument heats the samples to high temperatures, often above 800 degrees Celsius, 1472 degrees, to release volatile compounds present in Martian soil or rocks. The gases produced are analyzed by mass spectrometry, a technique that allows the identification of molecules and the quantification of their isotopes. Precision is crucial. It is important to verify that the rover's materials have not contaminated the samples, and that the analysis takes into account the low Martian atmospheric pressure, as well as potential soil oxidation. The 7 samples, showing a low ratio of carbon-13, stand out markedly from the known average profile, suggesting a particular event or process responsible for this isotopic alteration. It is important to note that on Earth, biological activity is not the sole cause of unusual isotopic signatures. Some abiotic geochemical phenomena, such as hydrothermal reactions, can also alter the ratio between carbon-12 and carbon-13, for example, by preferentially trapping carbon-12 in mineral precipitates. A Martian equivalent of these geothermal processes may have existed during the planet's ancient history, which experienced intense volcanic activity and hydrothermal sources. The scientific community therefore carefully compares the stratigraphy of rocks, the presence of clays or minerals indicative of ancient conditions, as well as the overall chemical environment inferred from these deposits. Another major nuance concerns the evolution of the Martian atmosphere. Mars has lost a significant portion of its atmosphere due to solar wind. On Earth, the magnetic field protects the upper atmosphere, but on Mars, the absence of a global magnetic field exposes the upper layers more. Isotopes can escape differently depending on their mass. It is possible that a preferential escape of carbon-13 into space left a relative enrichment of carbon-12 in some sediments. This hypothesis is being studied, but it does not seem sufficient to explain the very marked imbalance observed in the 7 samples. Nevertheless, it could play a secondary role in the history of the Martian crust composition. The parallel with terrestrial biological signatures is particularly tempting. On our planet, the study of carbon isotopes has identified traces of bacteria over 3 billion years old. Ancient rocks rich in fossil organic matter show a marked depletion in carbon-13, characteristic of biological fractionation. Observing such fractionation in Martian rocks arouses great interest. However, interpretation remains complex. Affirming a biological origin would require complementary evidence, such as microfossils, tissue structures, or carbonate patterns formed by microbial colonies. At this stage, scientists consider this promising discovery as an invitation to continue future analyses and missions to obtain more solid evidence. Understanding the distribution of this carbon-12 enrichment in the Martian stratigraphic column is essential. If these values are found in sedimentary layers corresponding to a period when Mars was warmer and wetter, it would reinforce the hypothesis of microbial life, as a wet environment promotes prebiotic chemistry and the emergence of simple organisms. Conversely, if these signatures are present in more recent layers, other explanations such as photolysis, cometary inputs, or active geological processes would gain credibility. This scientific puzzle requires that each discovery be precisely integrated into the global history of Mars. When the news of these 7 samples with a low carbon-13 ratio was announced, the excitement was high within the scientific community. Researchers from NASA and elsewhere sought analogies with terrestrial samples, notably very ancient rocks from Australia or Greenland, displaying similar isotopic anomalies interpreted as the oldest signatures of life on Earth. Comparing Martian cores to these terrestrial rocks over 3 billion years old can help identify subtle differences or support a biological scenario. However, caution remains. Mars and Earth have followed very different trajectories, with distinct climates, magnetic fields, and internal dynamics. Phenomena unknown on Earth could therefore have occurred on Mars. The fact that enrichment in carbon-12 was detected in 7 different samples is not insignificant. This indicates either a global process affecting multiple sites or multiple local phenomena producing a similar result. Geologists are trying to determine if these samples come from identical strata or various geological contexts. If they come from ancient lacustrine or fluvial sediments, the connection with liquid water and chemistry conducive to life is strengthened. On the other hand, if some come from volcanic or aeolian deposits, the biological origin seems less likely, as these environments can generate abiotic isotopic fractionation. Beyond these hypotheses, the presence of carbon-12 enrichment on Mars fuels the hope that the red planet may have once harbored microbial life. Other instruments on board rovers or in orbit continue the study of the planet. Future missions, particularly those aiming to return Martian samples to Earth, will offer the possibility of more precise analyses, notably on the isotopic distribution of carbon and other elements like sulfur, nitrogen, or iron. These investigations will seek indisputable geochemical markers of ancient biological activity. For now, this discovery remains open to several interpretations: intense ultraviolet photolysis, cometary inputs rich in carbon, or fragile clues of past life adapted to a once more hospitable environment. This scientific adventure reminds us that every clue, every anomaly, can be an essential piece of the puzzle of life beyond Earth. The story of carbon isotopic composition on Mars is still being written and is progressively enriched thanks to the efforts of Curiosity, its successors, and future missions. Observing this imprint of carbon-12 enrichment brings us back to fundamental questions. Is life a phenomenon unique to Earth, or does nature hold other examples of biological emergence in the solar system? The quest continues, and the careful study of ratios between carbon-13 and carbon-12, as subtle as they may be, could bring us closer to a major step in understanding our place in the universe. Radar and brines under Martian ice. This subject fascinates both specialists and curious minds about the mysteries of Mars. To grasp the issue, one must go back to 2003, when the European Space Agency launched Mars Express, a probe designed to explore the red planet in various aspects. Among its instruments is a radar named MARSIS, acronym for Mars Advanced Radar for Subsurface and Ionosphere Sounding. This device emits electromagnetic waves that penetrate the Martian ground, bounce back from different layers, and are then captured by the antennas of the probe. Its main goal is to reveal the internal structure of Mars, from the surface layers down to a certain depth, and potentially detect pockets of liquid water. In 2018, scientists analyzed Mars's data above the South Polar ice cap. They discovered bright echoes, meaning signals reflected with exceptional intensity. Typically, an intense echo signals a very smooth surface or a material with distinct properties. Here, these echoes indicate a very reflective interface buried under the ice. Researchers then suggested the possible presence of liquid water. This hypothesis is all the more surprising, given that Mars is currently very cold, with a thin atmosphere dominated by carbon dioxide. Polar temperatures can drop well below minus 120 degrees Celsius, or minus 184 degrees Fahrenheit, which makes liquid water improbable under standard pressure and temperature conditions. This is where the concept of brine comes into play. Water loaded with concentrated salts, like sodium chloride or magnesium perchlorate, capable of lowering its freezing point. The higher the salt concentration, the more water can remain liquid at extremely low temperatures. Scientists have therefore considered that the echoes detected by Mars might come from highly salty water pockets trapped between ice and rock. This water, thanks to its high salt content, could withstand the polar cold. Several studies have attempted to assess the salt concentration under the cap. Some suggest that the temperature there might be slightly higher than on the surface due to Mars's internal heat or the pressure of the ice. Despite this slight warming, the presence of pure water seems improbable. It is brine that keeps the debate alive. With high salinity, water could remain liquid despite temperatures of several tens of degrees below zero. But the debate doesn't stop there. Some researchers propose that these echoes could come from mineral or rock layers rich in iron, which are highly reflective to radar waves. Others mention a particular ice structure capable of generating intense reflection. To clarify, the variation of the echoes according to the radar angle and depth has been studied. Initial interpretations favor an interface between ice and a different material, potentially liquid or saturated with water. The controversy mainly concerns the conditions necessary to maintain this brackish water body. Temperature remains a key factor. Researchers are modeling Martian geothermal activity to estimate the heat emitted from the core to the surface. For very salty water to remain liquid, a slightly more temperate internal temperature is required. The ice cap could act as an insulator, retaining the heat from the subsurface. In some cases, the pressure of the ice and its thickness would favor the existence of water pockets at about minus 20 or minus 30 degrees Celsius, or minus 4 or minus 22 degrees Fahrenheit. This extreme cold would nevertheless be compatible with a liquid state thanks to the high salinity. Furthermore, the chemical composition of this water raises questions. On Earth, subglacial lakes like Lake Vostok in Antarctica have revealed a liquid environment, sometimes inhabited by extremophile microorganisms capable of surviving in the dark, under high pressure and with few nutrients. By analogy, some are questioning, if similar lakes exist on Mars, could microbial life have developed there? This question evokes great enthusiasm. If Mars harbors or has harbored liquid water under the ice, even intermittently or in small pockets, the possibility of life there gains credibility. Extreme environments on Earth show that life can adapt to hostile conditions. Bacteria could use the brackish water to survive, drawing their energy from dissolved chemical compounds. These life forms would likely be microscopic, as the limited availability of nutrients and absence of light restrict more complex organisms. However, caution is still warranted. These radar echoes could be misleading. Several models suggest that surfaces rich in certain minerals, such as clays or iron oxides, could strongly reflect radar waves. Others mention a strong anisotropy of the ice, meaning a specific orientation of the crystals, which could create a mirror effect. Confirming the presence of brines will require other methods or instruments. Several avenues are being considered for the future. New missions equipped with high-resolution radars could penetrate the ice more precisely and detail the internal structure of the caps. Orbiters equipped to measure local gravity could detect variations caused by water pockets. A more ambitious project would involve landing a module near the pole to drill through the ice to the suspected layer, an immense technical challenge with contamination risks and major logistical difficulties. Despite these uncertainties, the discovery of bright echoes has opened up an exciting field. Even without liquid water, this hypothesis has directed research toward Martian brines and the complex chemistry of salts. It is known that perchlorates are present on the surface, particularly near the North Pole, thanks to analysis by the Phoenix lander. These salts lower the freezing point of water, explaining their possible role in the presence of liquid water either deep down or on the surface. Radar data now suggests a strong concentration under the south polar cap. If these brine pockets exist, their size remains unknown, ranging from small basins to larger subglacial lakes. It is remarkable that an orbital radar, several hundred kilometers or miles away, detects signals of this nature, demonstrating the sensitivity of Marsis and the complexity of the phenomena being studied. As for the possible presence of life, scientists remain cautious. Demonstrating the existence of active microorganisms would require direct sampling. Nevertheless, the idea of an ecosystem isolated for billions of years in marginal conditions offers a fascinating perspective on the evolution of life in the universe. It is unknown if Martian life ever existed, but if these brines harbor microbial forms, the discovery would be a major breakthrough in astrobiology. Even in the absence of life, understanding these brines enriches our knowledge of Martian geophysics. How does internal heat circulate through the cold crust and ice? What fluid flows traverse the subsurface fissures? What reserves of salts does the planet retain since its formation? Each answer brings us a little closer to understanding Mars, its past, and its evolution. The matter remains open. The future of space missions will accompany this quest. Meanwhile, Mars's data continues to provide new clues to be cross-referenced with those from other instruments, other orbiters, and perhaps one day with robotic or human missions to the heart of the Martian ice. On the red planet, each discovery sheds a bit more light on its complex history, and the existence of a subglacial environment might well be the most captivating promise of recent years. If these brines are proven, they could reveal what we have long sought: unique geological archives and possibly the trace of a microscopic world hidden beneath the south polar cap. We approach one of the major mysteries of Martian exploration: the appearance of dark streaks descending some slopes, known as recurring slope lineae. Detected in 2011 by the high-resolution camera on the Mars Reconnaissance Orbiter, these brown streaks seem to appear and then vanish with the warm seasons. For several years, they were considered a major indication of the presence of salty liquid water on the surface of Mars. Detecting water on Mars has always been a crucial objective for researchers. The presence of a trickle of water, even loaded with perchlorate salts or other minerals, raises the hope of discovering traces of life, even microscopic. Imagine a dry environment, with temperatures ranging from nearly minus 120 degrees Celsius, or minus 184 degrees Fahrenheit, to about 20 degrees Celsius, or 68 degrees Fahrenheit, near the equator in summer. In this context, the discovery of these dark slopes associated with a potential water flow aroused strong emotion. Initially, several teams mentioned the possibility of brine tears, that is to say, flows of salty water on the slopes during the warm season. This hypothesis was based on spectroscopic clues revealing hydrated minerals. It was then imagined that these minerals, by absorbing a slight humidity, could create a very dense aqueous mixture. In this case, these dark streaks would constitute strong evidence of the temporary presence of liquid water. The preference for salt water is explained by the very low atmospheric pressure on Mars, around 6 millibars on average, much lower than that of Earth. In such an environment, pure water freezes or evaporates quickly. The salts present, like calcium, magnesium, or sodium perchlorates, lower the freezing point of water. Thus, at negative temperatures close to minus 50 degrees Celsius or minus 58 degrees Fahrenheit, small amounts of brine could remain liquid. For nearly a decade, the dominant interpretation suggested that these dark lines, visible on certain steep slopes, indicated the presence of salty water in the form of thin trickles. This idea, widely publicized, fueled hopes of a potential habitat for life, especially microorganisms. Some researchers then recommended specialized robotic missions to examine these dark slopes and collect samples. Investigations intensified with the analysis of color, brightness, and temperature variations over several years. As more images accumulated, it became apparent that these lines did not necessarily follow the behavior of liquid flows. They often seemed to coincide with the movements of dust or sand grains. Furthermore, if liquid water were present in significant amounts, more evident spectral signatures should have been detected. However, multiple observation campaigns did not confirm the formation of brine on the surface. The study published in Nature Communications in 2025 marked a decisive turning point. After compiling and analyzing a large number of detailed images, an international team concluded that most of these dark slopes would result from granular phenomena, in other words, flows of dry dust. According to this work, gravity and the dynamics of fine particles would be sufficient to explain the evolution of these traces without aqueous intervention. To achieve this result, scientists used a granular flow model applied to Martian dunes and slopes. They compared pictures taken at different seasons, looking for chemical signatures related to water. The data did not show the presence of saline fluids. On the contrary, they revealed that the repeated movement of dust particles, accentuated by thermal variations and sometimes light winds, could create these dark patterns. This effect gives the illusion of liquid seepages. This new explanation suggests that the initially suspected tears of brine would, in most cases, be non-existent. The possibility of microscopic small volumes of water formed during favorable moments is not entirely ruled out. However, if they exist, they are much rarer and more limited than previously imagined before the 2025 study. The researchers point out that Martian dynamics could locally generate humidification phenomena, but they remain fleeting and difficult to detect. This revision has significant implications for the search for life. On Earth, the presence of liquid water is an essential criterion for living organisms. Even in extreme conditions, such as highly saline or cold environments, the near disappearance of tiers of brine on Mars prompts a redefinition of scientific priorities. From now on, the focus is more on the subsurface, where the presence of stable water or ice seems more probable. The Martian surface is exposed to a high level of radiation in the absence of an active global magnetic field. This exposure complicates the survival of microorganisms in the superficial layers. Moreover, the thin atmosphere, dominated by carbon dioxide, does not protect against sharp thermal variations. Researchers suspect that a few meters or tens of meters, 3 to 33 feet, below the surface, the temperature would be more stable and the radiation lower. An underground habitat thus remains conceivable, even in the absence of visible streams. The future prioritization of subsurface life targets, according to several teams, rests on the growing interest in drilling and the search for natural cavities. Robotic missions equipped with more efficient drills and small exploratory vehicles capable of entering tunnels or shafts are being developed. These initiatives aim to probe the deeper layers of the Martian soil in search of organic molecules or microfossils preserved from chemical destruction on the surface. The question of water on Mars is thus reevaluated in light of these discoveries. If these dark slopes are mostly the result of dust flows, we cannot exclude the formation of thin, moist layers from frost melting or temporary condensation of atmospheric humidity. Such occurrences could occur at dawn or in shaded crevices, but they seem incapable of supporting a sustainable habitat. In this context, Martian exploration focuses on more reliable indicators of past or present subsurface water. Future missions, equipped with radars, will continue to assess the composition and structure of deep geological layers. The data suggests the possible existence of pockets of ice or brine trapped beneath the surface. If the surface is too hostile, the subsurface could offer slightly more favorable conditions, with sometimes temperatures above 0 degrees Celsius or 32 degrees Fahrenheit. Imagine a journey through the cold and arid deserts of Mars, where the wind lifts fine orange and red particles and the sky turns pink at dusk. Behind this frozen landscape lie particular chemical compounds, perchlorates. This term indicates a possible link between the inert chemistry of the red planet and an energy source for potential microorganisms. In this story, we will discover what these perchlorates are, why they have aroused so much interest among scientists since their detection, and how several robotic missions have identified them. We will also discuss their implications for possible forms of life, even rudimentary, in Martian soil. To understand, let's first define perchlorate. On Earth, a salt is generally the combination of a metal, such as sodium, potassium, or magnesium, with a negatively charged element or group of elements. Perchlorates associate a metal with a group consisting of 1 chlorine atom and 4 oxygen atoms. This oxygen-rich chemical group can combine with different metals, giving, for example, calcium, sodium, or magnesium perchlorate. The discovery of these molecules on Mars results from years of preparation and complex missions aimed at better understanding the planet's chemistry, notably to detect the presence of water and possible signatures of life. It all begins in 2008 when the Phoenix lander touches down near Mars's North Pole. Equipped with a laboratory to dig and analyze the soil, Phoenix detects unusual salts that turn out to be perchlorates. This discovery intrigues the scientific community because these compounds, known in some extreme environments on Earth, had never been observed on another planet. The mission of the rover Curiosity, which arrived in 2012, confirms the widespread presence of perchlorates in various samples collected in the Gale crater. The analysis reveals sodium, magnesium, and sometimes calcium perchlorates. This finding raises a key question. If these compounds are widespread, what role do they play in Mars's geological and potentially biological history? Ongoing research aims to map their distribution across the planet. A report expected in 2024 should provide a global inventory of their presence and abundance by region. To grasp the interest in perchlorates, one must briefly discuss chemistry and biology. On Earth, certain perchlorate-reducing bacteria exploit these compounds to produce energy. This process relies on redox reactions, a reaction used by many microorganisms to extract the energy necessary for their survival by using compounds containing oxygen. While the oxygen from the air is the best-known molecule, some microbes use other compounds, such as nitrates, sulfates, or perchlorates, particularly in environments poor in oxygen. When a microbe degrades a perchlorate, it progressively loses oxygen atoms, thus releasing usable chemical energy. The chlorine-oxygen group then transforms into less oxygenated compounds or even into chloride, depending on the reaction stages. This strategy allows these microorganisms to survive in oxygen-poor environments. On Mars, where the atmosphere contains little oxygen and the climate is cold and dry, the abundant presence of perchlorates could offer an energy lever to potential Martian microbes, past or present. Perchlorates also have the ability to retain moisture and form brines, highly salted water solutions. On Mars, temperatures can drop to -60 degrees Celsius or -76 degrees Fahrenheit, but reach around 20 degrees Celsius or 68 degrees Fahrenheit in some equatorial areas during summer. These salts lower the freezing point of water, allowing it to remain liquid at very low temperatures. This property arouses great interest, since even a brief presence of liquid water is a crucial factor for the emergence and survival of living organisms. However, it is important to qualify this. Martian chemistry is very aggressive. Solar radiation is intense, the planet lacks a global magnetic shield, and the soil contains other oxidizing compounds. It is therefore not certain that microbes can thrive easily. In laboratories, researchers recreate Martian conditions, combining high salinity, low pressure, and temperatures close to -50 degrees Celsius or -58 degrees Fahrenheit. They then introduce Earth microbes adapted to cold and salinity to study their ability to use perchlorates as an energy source. Certain terrestrial bacteria, particularly from extreme environments such as salt lakes or polar regions, tolerate high concentrations of perchlorates. They can even exploit the reduction of these salts to produce their energy. But these results are not directly transposable to Mars, where radiation levels, drought, thermal variations, and the rarity of organic molecules make the environment very hostile. Nevertheless, the existence of these organisms on Earth opens up the possibility that Martian microbial life may have used this chemistry. Practically, the synthesis scheduled for 2024 will compile data collected by orbiters and rovers over the last 20 years. These instruments detect specific mineral signatures based on the light reflected or absorbed by the surface. Each type of salt has a distinct fingerprint. This refined mapping will make it possible to target areas where perchlorates are most abundant in order to guide future robotic missions in search of signs of biological activity. It should also be noted that perchlorates influence the analysis of organic molecules on the surface of Mars. Instruments that heat samples release oxygen from the decomposition of perchlorates, which can oxidize and destroy any organic molecules present, making their detection more difficult. It is, therefore, essential to consider this interaction before concluding the absence of organic matter. Over the course of missions, Martian chemistry reveals its incredible complexity. As early as the 1990s, the Viking probes had shown an oxidizing soil, but its nature remained mysterious. With Phoenix and then Curiosity, the presence of perchlorates is now confirmed in several regions, forcing a revision of our knowledge of Mars's surface, history, and biological potential. Finally, imagine a hypothetical Martian habitat, several meters or yards below the surface, protected from wind and radiation, with a thin layer of perchlorate brine. Thanks to perchlorate's ability to keep water liquid at very low temperatures, a microbe, comparable to those from Earth's glacial lakes, could survive, deriving its energy from the reduction of perchlorates to grow slowly. This scenario, although speculative, motivates current research. It should also be remembered that perchlorates are not solely allies. They are toxic, disrupting, for example, the thyroid in humans. Human exploration projects, therefore, include protections against these salts. However, they remain interesting for the exploitation of local resources, such as fuel production or industrial chemistry. On Earth, some perchlorates are used in pyrotechnics to release oxygen under heat. On Mars, these properties could be used to make fuel or support breathing in closed habitats, although these ideas remain theoretical for now. While waiting for the 2024 synthesis to be published, research continues to explore the formation of perchlorates, whether from local interactions under ultraviolet radiation, atmospheric processes, or concentration in ancient lakes. The role of dust storms in their global distribution is also being studied. For the future, robotic missions dedicated to this chemistry are envisioned. The idea would be to send a rover capable of drilling deeper, taking soil cores rich in perchlorates, and checking for the presence of liquid water several meters or yards deep. Softer analysis instruments, limiting sample decomposition, would be designed to better detect potential organic compounds. In the heart of the vast, icy expanses of Antarctica, researchers have unearthed one of the key elements of the Martian enigma, a rock named Allen Hills 84001. This name, although seemingly technical, refers to both the location of its discovery, Allen Hills, and the approximate year it was found, 1984. This meteorite, often abbreviated as ALH 84001, quickly sparked a global scientific debate, especially starting in 1996. A team from the American Space Agency had then suggested that this rock could contain clues of primitive Martian life. The media widely circulated images of minuscule structures resembling microfossils, sparking immense hope, that of a first proof of extraterrestrial life, even if it had disappeared billions of years ago. To grasp the origin of this controversy, it is essential to understand what a Martian meteorite is. It is a rock originating from Mars, expelled due to a violent impact, often caused by the fall of an asteroid or a comet. The explosion projected fragments of the Martian surface into space, where they drifted for thousands, if not millions of years, until they encountered Earth. As they passed through its atmosphere, these fragments became meteorites, which are sometimes found in icy deserts like Antarctica or in drier desert regions. Holding a rock from another planet in one's hands already represents an achievement that fuels the imagination. The meteorite, ALH 84001, distinguished itself by its chemical composition and the presence of particular mineral structures. It notably contains deposits rich in carbonates. These compounds, also present on Earth, result from the association of carbonate ions with elements such as calcium, magnesium, or iron. We talk here about globular carbonates forming small grains or mineral spheres inside the rock. On our planet, similar carbonate deposits, like those in reefs or caves, are sometimes linked to biological processes. The first analyses revealed in these globular carbonates microscopic structures resembling filaments or flattened tubes. In 1996, a team led notably by David McKay put forward a revolutionary hypothesis. These elongated formations could be fossilized bacteria. Researchers also noted the presence of organic molecules, that is, carbon-based within the meteorite. In the mind of the scientific community, these molecules could represent a biological signature. On Earth, numerous living beings leave organic traces or modify the chemistry of their environment. This announcement provoked great excitement relayed by the media worldwide, suggesting that ancient life on Mars might have been discovered. The debate had just begun. The interpretations quickly diverged. Some considered the tubular shape of the structures, associated with the presence of carbon-based molecules, as a plausible proof of ancient microbial metabolism. Other researchers remained cautious, noting that geological processes could explain these observations. They reminded that organic molecules can form inorganically, via chemical reactions without biological intervention. For instance, interactions between water and certain rocks under specific temperature and pressure conditions can lead to the synthesis of complex molecules without any microorganism involved. At the center of the controversy is also serpentinization. This geological process occurs when rocks rich in ferromagnesian minerals, like olivine, come into contact with water. At high temperature and pressure, this reaction produces molecular hydrogen and other compounds that can combine to form various types of organic molecules. On Earth, this mechanism plays a role in the formation of submarine hydrothermal vents, habitats for microbes using hydrogen as an energy source. Imagining a similar process on Mars raises the question: if the planet had enough liquid water and the right conditions, could these reactions have created organic molecules without the existence of life? Thus, detecting such molecules is not sufficient to prove a biological origin. Moreover, the globular carbonates in ALH 84001 can be explained by geological phenomena. These carbonates often form when fluids pass through a rock and precipitate minerals, leaving deposits. On Earth, we find complex carbonate formations, sometimes linked to life, sometimes purely abiotic. Laboratory experiments have shown that it is possible to produce structures resembling microfossils without bacteria. This difficulty makes distinguishing between biological relics and abiotic processes complex, requiring years of study and multiple analyses. Between 1996 and 2022, the controversy underwent several phases. New instruments enabled more precise examinations. High-intensity X-rays revealed details of the internal texture of the carbonates and the distribution of elements such as oxygen, iron, magnesium, or sulfur. Advanced imaging techniques showed that some presumed fossil structures were too small or morphologically ambiguous to be identified as microorganisms. Gradually, the idea of a non-biological origin gained traction. At the same time, it became apparent that the organic molecules in ALH 84,001 might arise from abiotic reactions. Studies published in various journals, notably Science News and EOS, highlighted the synthesis of carbon molecules via serpentinization or other high-temperature chemical processes. The hypothesis of an organic input from space, via asteroids or comets, also remains plausible. It is worth remembering that the early solar system was subject to intense bombardment, potentially dispersing organic compounds across multiple planets, including Mars. Another crucial point concerns the measurement of carbon isotopes, which examines the distribution of different forms of this element in the rock. On Earth, living beings prefer lighter carbon, carbon-12, rather than heavier carbon-13. This preference creates isotopic signatures characteristic of biological processes. In the meteorite, analyses attempted to determine whether these isotopes corresponded to terrestrial microorganisms or rather to geological reactions. The results remained ambiguous. Some evidence showed a slight enrichment in lighter carbon, favoring the hypothesis of ancient life, while others pointed out that inorganic processes could generate similar signatures. Over time, the majority of researchers have come to the conclusion that the structures observed in ALH 84,001 are not fossils of Martian life. The micro-images of elongated forms were never confirmed as exclusively biological. Numerous studies have shown that abiotic phenomena, such as the precipitation of minerals in small channels, can create patterns resembling fossilized cells. In 2022, scientific syntheses concluded that there is no definitive evidence of Martian life in this meteorite. Nonetheless, the story of ALH 84,001 is not merely one of disappointment. This meteorite has stimulated exobiology, the science that studies life beyond Earth. Each new technique used to analyze its composition paved the way for more advanced methods, such as mass spectrometry, electron microscopy, or X-ray diffraction. The data from this rock have fueled numerous articles, debates, and initiatives to search for evidence of life in the solar system. Interest in Martian meteorites has not been limited to ALH 84,001. Other fragments discovered since have been meticulously analyzed. Sometimes they contain strange mineral inclusions or small amounts of organic compounds, reviving the question, do they have a biological origin? Each time, rigorous analysis is necessary, examining the structure of the minerals, studying the isotopes, and distinguishing what might come from microbial activity from what is a result of natural chemistry. In most cases, geochemistry is sufficient to explain the presence of the molecules and crystallizations without involving life. Beyond these meteorites, research explores how Mars could have produced or hosted organic compounds. Inorganic organic sources refer to natural reactions capable of synthesizing carbon-based molecules without life. Serpentinization remains a key mechanism, producing hydrogen that can fuel organic synthesis. Even though water is rare on Mars today, it is possible that the planet once experienced hot water circulations in its crust, creating complex chemistry at the threshold between mineral and organic. In 2022, several studies highlighted the need to reevaluate each clue and systematically compare biological hypotheses to abiotic scenarios. This caution limits hasty interpretations and keeps the debate open. Many experts acknowledge that the controversy surrounding ALH 84,001 has strengthened scientific rigor, proving the discovery of fossil life traces will now require gathering a solid body of evidence, from mineral analysis to isotopic measurements, without neglecting geological alternatives. Despite this evolution, ALH 84001 and the meteorites that followed remain major references in the quest for life on Mars. They offer tangible samples that can be studied in the laboratory, unlike data collected by orbiters or rovers. Handling these fragments allows us to recreate conditions similar to those that may have existed on Mars and to examine how certain compounds form. The chemical processes mimicking life are numerous, making a critical approach indispensable. The great lesson of ALH 84001 is clear. Detecting life, even fossilized, requires caution and the accumulation of converging evidence. Today, most research favors a geochemical explanation for the anomalies of ALH 84001 rather than a microbial origin. Yet, this story doesn't end there. The debates have led to the improvement of investigative methods. Future missions, both robotic and human, will aim to return Martian samples to Earth with rigorous traceability. Thanks to the knowledge gained from the controversy, these new materials will be analyzed with an increased capacity to distinguish abiotic chemistry from biological signatures. We are now at one of the most crucial moments in Martian exploration, the prospect of returning samples taken directly from the surface of the red planet to Earth. Imagine the scene. The Perseverance rover, sent by the American Space Agency, moves slowly over the dusty soil of Mars. It drills into the rock, extracts small cylindrical cores, and then places them in hermetic tubes. These metal cylinders, designed to withstand the extreme conditions of Mars, herald a new scientific chapter. They constitute the first rigorously selected collection of Martian rocks intended for analysis in the most advanced laboratories on our planet. This true geological treasure could reveal crucial information about Mars's chemical composition, its distant past, and the possible presence of life traces. But this endeavor goes beyond a simple round trip. It represents the culmination of decades of research, planning, and technical innovations to master the complex logistics of returning Martian samples to Earth. To grasp the strategy, one must first mention the choice of Jezero Crater as Perseverance's landing site. Scientists unanimously agreed that this crater, rich in varied geological formations, offered the best chance of finding clues about the planet's ancient habitability. This place was not chosen at random. It houses a well-preserved fossil delta, once formed by a watercourse. Its numerous diversified sedimentary layers are particularly conducive to searching for geochemical signatures linked to potential microorganisms. In this context, the rover methodically collects samples, storing them in airtight tubes. Some samples have predominantly sedimentary content, while others are more basaltic or clayey. This variety ensures a complete view of Martian geology. The mission plans to collect up to 38 tubes, thus forming a true natural catalog, carefully prepared for future transport to Earth. The term caching refers precisely to the deposition of these samples on the ground at specific points meticulously recorded to allow their subsequent retrieval. Imagine a network of deposition sites, akin to stops on an itinerary, where each stop signals the presence of sealed tubes containing a fragment of Mars past. Engineers employ a system called Delta Launch Sample Acquisition System, or DLSAS, to handle the cores and permanently insert them in the tubes. This device ensures that the samples remain free from contamination, neither by Martian dust nor by terrestrial elements. Each operation is accompanied by precise recording, exact position, nature of the rock, environmental measurements, and preliminary analyses performed by the rover's instruments. Each tube thus tells a detailed geological story, consigned to be studied later on Earth. Let us come to the centerpiece of this return, the Mars Sample Return Mission, or MSR. This collaboration between the American Space Agency and the European Space Agency relies on several distinct vehicles: a rover tasked with retrieving the tubes, a launcher to leave the Martian surface, and an orbiter that will transport the cargo to Earth. Before considering the interplanetary return journey, the deposited cores must be retrieved. This task falls to the rover called Fetch Rover, the recovery rover. It will traverse the Martian surface to collect the tubes left by Perseverance. At this stage, reliability will be crucial. No tube must be lost or damaged. This requires a sophisticated tracking system, capable of locating the samples with a precision of a few centimeters or inches. The Fetch rover will be equipped with robust cameras, proximity detectors, and a robotic arm to delicately grasp each tube. Once the collection is completed, the Fetch rover will transport its precious cargo to a launch module installed on the surface of Mars. This launcher, called the Mars Ascent Vehicle, will have to break free from Martian gravity. Although it is about a third that of Earth, liftoff remains a major challenge. Engineers are designing a propellant capable of operating in the thin atmosphere, dominated by carbon dioxide and resisting extreme temperatures, well below -60 degrees Celsius or -76 degrees Fahrenheit. The success of this launch will determine the continuation of the mission. In case of failure, the samples would remain irretrievably on Mars. The Mars Ascent Vehicle will carry a container specially designed to withstand acceleration forces and the space environment before releasing it into Martian orbit. Then the Earth Return Orbiter, scheduled for launch towards the end of the decade with an orbital rendezvous around 2030, will intervene. This orbiter's mission will be to capture the container in orbit around Mars and then bring it back to Earth. It will be an unprecedented technical feat, requiring perfect synchronization to capture a fast-moving object and secure it in a storage system capable of traversing hundreds of millions of kilometers or miles. Upon arrival, a re-entry capsule will detach, penetrating Earth's atmosphere before landing in a dedicated and highly secured area. The schedule, with launches spread over several years and retrieval planned in the 2030s, illustrates the rigor necessary for such a mission. Each step must be validated to eliminate any risk. However, planetary protection remains a major concern, involving two aspects: preserving Mars from terrestrial contamination and preventing any Martian microorganisms from being accidentally introduced to Earth through this sample transfer. Since the beginning of exploration, international standards protect Mars against the introduction of terrestrial bacteria that would skew the search for indigenous life. Probes are sterilized and handled in controlled environments. Now, with the return of the samples, another concern arises: that unknown life forms, preserved in the rocks, might pose a risk to Earth's biosphere. That's why the MSR mission includes a strict biosecurity protocol. Once on Earth, the samples will be transferred to a high-protection laboratory, comparable to those where pathogens are handled. Specialists will analyze the rocks to detect any dangerous contamination. Even if this possibility seems unlikely given Mars's extreme conditions, caution prevails. Thorough tests will look for the presence of organic molecules, reactive chemical elements, or biological anomalies. Once safety is confirmed, scientists can begin an in-depth study of these materials with the most advanced instruments. Planetary protection also aims to preserve the very integrity of the samples. Back contamination refers to the risk of introducing terrestrial traces into Martian rocks that could alter their analysis. Each gram of Martian soil is an intact witness of the extraterrestrial environment. Even slight contamination could compromise this valuable data. The protocol thus includes multi-layer airtight packaging, handling in clean rooms, and rigorous decontamination techniques. Engineers are developing containers capable of maintaining a partial vacuum or a neutral atmosphere, ensuring the chemical preservation of the samples. This level of precaution is similar to that of the pharmaceutical industry, but with even higher scientific stakes. Another important aspect concerns the distribution of responsibilities. The American Space Agency, with its European partners, shares the tasks. The design of the Fetch rover mainly falls to Europe, while the Mars Ascent Vehicle launcher and the Earth Return Orbiter result from close collaboration. This division of expertise aims not only to distribute costs, but also to unite expertise, orbital guidance, structural robustness, communication reliability, and sample handling. This is a striking example of international cooperation in the service of science. However, the mission must contend with uncertainties related to timelines, budgets, and technical challenges. Each piece of equipment is tested in conditions close to those of Mars: vacuum, low temperatures, a carbon dioxide-rich atmosphere, increased radiation. Despite the complexity and cost, the scientific community believes that the stakes justify these efforts. Imagining that one day, an intact fragment of Mars will land on Earth evokes immense excitement. Laboratories will then have cutting-edge equipment, electron microscopes, ultra-sensitive spectrometers, X-rays, capable of revealing secrets billions of years old. The world thus eagerly awaits the effective start of this interplanetary bridge between Mars and Earth. Perseverance, already in action, has collected valuable cores. In the meantime, ground teams are preparing the Fetch rover and testing modules for the future Martian launcher. In space exploration, nothing ever goes exactly as planned, but each advance validates an essential link in this chain towards success. Planetary protection remains an evolving field. If new biological clues appear before the deployment of the Fetch rover, handling protocols might become more stringent. Specific areas like caves or deep pits could reveal the presence of life, requiring increased vigilance. This ethical rigor does not hinder determination. It underscores the importance of strong responsibilities in our explorations. Finally, the last step concerns terrestrial recovery. Engineers are already developing procedures for the recovery of the capsule and the management of the samples in the laboratory. Specialized teams will ensure handling in controlled environments, probably in a sterile hangar, under constant surveillance. Each step will be documented and analyzed to ensure safety. The scientific study will then really begin with the most precious material, authentic Martian rock, preserved in its almost original state. This caching strategy, followed by a multi-phase return, illustrates the complexity of such a mission. The 38 sealed tubes by Perseverance establish the beginning of a scientific link between Mars and Earth. They await the Fetch rover, which will gather them, the Mars Ascent Vehicle that will send them into orbit, and finally, the Earth Return Orbiter that will bring them back. Each step must work flawlessly. Upon completing this journey, it will be a significant leap in our understanding of Mars's history, its habitability, and possibly life in the universe. In the constant quest to understand Mars and its potential to harbor life, researchers have recently turned their attention to underground formations that could serve as natural shelters. These structures are sometimes referred to as caverns or lava tubes. While they might initially resemble caves similar to those on Earth, it is essential to remember that Mars's geological and environmental conditions are quite distinct. The exploration of these spaces, made possible by infrared imaging and orbital cameras, could someday offer a new perspective on the red planet. In this section, we will delve into the heart of these mysterious formations to understand their importance for future missions and their scientific value. We will also look into Themis imaging, which has revealed vast openings known as skylights, and discover the CAM CaveBot project, designed to explore these unique environments. First, it is important to define what a lava tube is. On Earth, these conduits form when large lava flows solidify on the surface, while magma continues to flow inside. Gradually, the evacuation of the lava sometimes leaves a hollow tunnel behind. On Mars, the massive volcanoes of the Tharsis region, once active, may have generated comparable structures. Given that the Martian formations are generally larger than terrestrial volcanoes, it's likely that these tubes are also vast, stretching for several kilometers or miles and reaching heights often greater than those observed on Earth. What has particularly captured scientists' attention are the openings spotted on the surface, particularly thanks to an instrument called Themis. This device, the English acronym for Thermal Emission Imaging System, observes Mars by detecting infrared radiation emitted or reflected by the ground, revealing temperature variations throughout the day. This method has identified zones with stable temperatures, indicating possible underground cavities. Among these discoveries are the skylights, natural shafts resembling large holes that grant access to a more expansive interior space. Some of these pits detected by Themis reach a diameter of about 35 meters or 115 feet, or even more. Imagining such a void in the Martian soil stirs curiosity. Researchers believe these skylights often result from the partial collapse of the roof of a lava tube. Initially supported by rock and solidified lava, the vault becomes fragile over time, particularly under the impact of ancient tectonic activities or thermal contractions. When the roof collapses, a chasm forms, allowing sunlight to enter the cavity. Viewed from the surface, this dark opening with sharp edges reveals the existence of a larger volume under the rock. A major interest in these caverns and lava tubes concerns temperature. On Mars, daily thermal fluctuations are extreme. It can be 0 degrees Celsius or 32 degrees Fahrenheit during the day in some regions, then plummet to minus 100 degrees or minus 148 degrees Fahrenheit at night, depending on latitude and season. These variations make life difficult for both potential organisms and technical equipment. Inside a lava tube, the temperature would be much more stable, averaging around minus 20 degrees Celsius or minus 4 degrees Fahrenheit. This cold remains severe, but significantly more hospitable than the surface conditions swept by freezing winds and devoid of a protective atmosphere. Beyond temperature, radiation protection is a key factor for future exploration. Without a magnetic field, Mars is exposed to solar and cosmic particles, which strike directly onto its surface. This bombardment is harmful to life and represents a major challenge for human settlement. Measurements indicate that the interiors of caves benefit from significant natural protection. The rocky ceiling reduces radiation exposure to less than 10% of that measured on the surface. This shield could be a decisive advantage for the survival of microscopic organisms or for establishing a base. Thus, thermal stability and radiation protection make lava tubes and caves preferred candidates for setting up Martian bases, whether robotic or manned. It is also possible that ancient microorganisms found refuge in these environments, protected over millennia. For biologists and exobiologists, these underground locations could be preserved niches where ancient life may have survived longer than on the exposed surface. Faced with this potential, the desire to explore these fascinating environments is natural. However, descending into a lava tube on Mars represents a considerable technical challenge. No equipment is yet in place, and accessing through a skylight and then exploring underground are complex operations. Existing Martian rovers are designed to operate on the surface, not to tackle steep slopes or navigate through cavities. It is in this context that the CAM CaveBot concept has emerged. Announced around 2025, the CAM CaveBot is a compact robot capable of moving autonomously or semi-autonomously, equipped with robust sensors adapted to Martian conditions. CAM stands for a module designed to map and analyze the environment. CaveBot means cave robot, specially designed to descend into lava tubes via skylights, explore galleries, collect samples, measure humidity, and detect organic molecules that could shed light on the geological and biological history of Mars. To accomplish this mission, the CAM CaveBot must perform several complex functions. It must first precisely locate the tube entrance, then descend without crashing to the ground. Methods like using cables, grapples, or drones with propulsion adapted to the Martian atmosphere are being considered. Inside, the near-total darkness requires efficient and energy-saving lighting. The robot will also have to tackle rough terrain, rubble, and dust that could affect its solar panels if they are not protected. Flights and landings on Mars are already perilous. Adding descent into an underground conduit increases the risk. However, the scientific gains are significant. A specialized rover could access protected geological samples, offering a historical sequence of volcanic activity and clues to possible water infiltration. If microbial life has existed or still exists, the CAM CaveBot could contribute to its discovery, paving the way for a major breakthrough in the search for extraterrestrial life, even fossilized or microscopic. Designing this type of mission involves crucial technical choices: wheeled rover, legged vehicle, or drones, power source, radioisotope generator, or solar panels. Analysis instruments and communication means to the surface, then to Earth, for a device that could be several tens of meters or dozens of feet underground. These challenges are the subject of prototypes and simulations, illustrating the complexity of this unprecedented exploration. On Earth, several teams are already testing robots in analogous lava tubes, notably in Hawaii or volcanic deserts. These trials in dimly lit environments with complex geometry allow for the development of adapted navigation techniques. Simultaneously, research on extremophilic bacteria in these environments informs the development of the CAM CaveBot. The milestone of 2025 marks a benchmark for the development of the concept, but the necessary progress could take several years, or even a decade, before a device is sent to Mars. Financial and technological constraints are high, and space agencies must prioritize their objectives. Nevertheless, Martian caves are garnering attention, as they could become a refuge for humans and preserve valuable vestiges of planetary history. When discussing the current climate of Mars, its striking contrasts and apparent hostility are immediately evident. Yet, behind these extreme conditions lie clues that spark significant interest in microhabitability. The study of temperature fluctuations, atmospheric composition, humidity, and seasonal phenomena reveals a complex world where water, in specific forms, could briefly emerge. In this section, we will clearly and thoroughly describe the climate gradient between the equator and the poles, the issue of relative humidity exceeding 60% at night, the seasonal appearance of carbon dioxide frost, and finally, the possibility of translucent salty water films forming at dawn. All of this is to better understand the notion of microhabitability, the ability of certain microorganisms to find favorable niches for the development of life. To begin, it is essential to grasp the general nature of the Martian climate. Mars, being farther from the Sun than Earth, receives less solar energy. Its atmosphere, very thin and dominated by carbon dioxide, lacks the pressure necessary to retain heat efficiently. This results in significant temperature variations throughout the day and across different locations. Near the equator, the temperature can reach 20 degrees Celsius, 68 degrees Fahrenheit, during the day, dropping to minus 70 degrees, 94 degrees Celsius, the following night. At the poles, conditions are even more extreme, with areas dipping below minus 120 degrees, 184 degrees Celsius, during the local winter. This broad thermal range, often referred to as the equator to pole gradient, strongly influences the distribution of water on the surface and in the atmosphere by modulating the air's capacity to hold water vapor. Relative humidity is a critical factor for assessing the potential presence of liquid or solid water. On Earth, this concept measures the proportion of water vapor in the air relative to its maximum capacity, which varies with temperature. On Mars, despite a very low absolute quantity of water vapor, relative humidity can exceed 60% at night. This phenomenon is explained by the rapid drop in nighttime temperature, which reduces the air's capacity to hold water vapor, causing a relative increase even in a very dry environment. However, a high relative humidity level does not necessarily mean a significant presence of liquid water. The Martian atmospheric pressure is generally too low for water to remain stable in a liquid state on the surface, except in very specific cases or sheltered by certain geological structures. Most often, water vapor condenses directly into frost or ice without a lasting liquid phase. This reality complicates the survival of life as we know it, as most terrestrial organisms require liquid water for vital biological functions like photosynthesis or metabolism. A remarkable phenomenon on Mars is the seasonal formation of carbon dioxide frost. Unlike Earth, where frost is primarily ice from water, Mars regularly sees the appearance of frost composed of carbon dioxide, especially during the coldest nights or in winter. This gas, which is the majority in the Martian atmosphere, condenses into a solid form at temperatures often below minus 120 degrees Celsius, 184 degrees, covering the surface with a thin whitish layer akin to dry ice snow. This frost can extend over plains, dunes, and ridges, giving the landscapes a polar appearance even at lower latitudes. This frost quickly sublimates with the sunrise, as a slight rise in temperature transforms the solid carbon dioxide into a gas. This process sometimes generates visible movements, such as dark flows on slopes where the ice displaces the dust. Climatically, this seasonal sublimation fluctuates atmospheric pressure. When polar caps accumulate frozen carbon dioxide, the atmosphere temporarily loses gas. Conversely, sublimation slightly increases pressure, which still remains far below that of Earth. A major point of interest for researchers is the possible ephemeral appearance of liquid water, even for a few moments. Despite the low pressure that tends to make water transition directly from solid to gas, the presence of specific salts in the soil can lower the freezing temperature. A brine, a mixture of water and salts, can remain liquid at temperatures well below those of pure water. Different salts, such as perchlorates or chlorides, have been identified in the regolith, making the formation of thin layers of salty water plausible. The opportune moment for these brine films to form is in the early morning, when the temperature is just starting to rise but the ground remains very cold. The first rays of sun then warm the surface enough to briefly liquefy this salty ice before it evaporates or refreezes. These translucent films of salty water, almost invisible, disappear quickly with the increase in warmth. Their detection remains difficult, as they are likely sporadic, located in shaded areas or depressions that slightly maintain heat. Nonetheless, this hypothesis remains an important research subject, as even a brief presence of liquid water, however salty, opens prospects for the possible survival of microorganisms. The concept of Martian microhabitability relies on the ability of certain microorganisms to maintain an active metabolism in these extreme environments. On Earth, extremophile bacteria and archaea tolerate high salinity conditions, intense cold, and exposure to radiation. On Mars, the transient presence of liquid water could offer a niche for such forms of life, stemming from a distant past or still active. However, it should be noted that the existence of these films of salty water has not been demonstrated on a large scale. The very low volumes of water mixed with salts are difficult to detect. High-resolution images from orbiters and rover measurements seek to provide indirect evidence, such as localized humidity variations or changes in ground brightness at dawn or dusk. The rapid fluctuations of surface temperature complicate data collection. Nevertheless, research is progressing, enriching our understanding of Martian water dynamics. Conversely, the fact that relative humidity can exceed 60% at night remains a crucial element. This phenomenon does not correspond to fog formation as on Earth, as the absolute water vapor is extremely low. It's an effect related to low temperature and reduced atmospheric pressure. In rock cavities or beneath the surface, condensation could be accentuated by thermal trapping. For example, a small dark depression accumulates heat during the day and slowly releases it at night, thus limiting complete freezing or rapid condensation. In these niches, humidity may be more significant than on exposed plateaus. In the long term, the instability of the Martian climate, marked by large daily variations in seasonal cycles, influences microhabitability. The seasonal formation of carbon dioxide frost dries the atmosphere, as this frost contains no water, temporarily reducing pressure and water vapor. At the same time, slight diurnal heating may promote the local dilution of salts in thin traces of water, modifying the freezing point and favoring a brief persistence of liquid water. Thus, Mars presents a contradictory climate, hostile by its extreme cold, low pressure, and tenuous atmosphere, but favorable to the creation of liquid micropockets due to brine properties. Current research relies on data collected by rovers and orbiters measuring water vapor, soil temperature, and relative humidity dynamics. Projects are considering the installation of specific sensors to detect fleeting traces of liquid water, whether from condensation or differentiation between water ice, carbon dioxide ice, and brine. Future Martian vehicles could refine these observations, particularly in more temperate areas, by studying the interaction between soil and water. For manned exploration, microhabitability raises issues of contamination. If terrestrial microbes were to temporarily colonize these salty films, it would become difficult to distinguish Martian life from contamination from Earth. Sterilization protocols are therefore very strict when landing in these areas. Conversely, for astronauts, the presence of water, even very salty, could be a valuable resource, provided it is filtered and treated. It would not be the ideal solution for a colony, but every local source of water is an advantage. From a scientific point of view, studying the current climate and its relationship with water offers a window into Mars's history. Once warmer and wetter, this planet probably hosted lakes and rivers. Today, only polar ice caps and fleeting traces of atmospheric moisture remain. Yet, this meager remnant paves the way for the search for a hidden microbial ecology and a broader understanding of planetary evolution. Imagine yourself in orbit around Mars, observing the darkness of the space surrounding it. Two small celestial bodies, one more imposing than the other, silently revolve around the red planet. Phobos and Deimos are often called the moons of Mars, but it is more accurate to refer to them as satellites. Their simple shape contrasts with Earth's moon. They do not have sharply drawn craters as one might imagine. Yet, behind this modest silhouette lies a major scientific promise. They may have accumulated over time Martian dust, possibly containing clues of ancient life or biochemical traces. To understand this issue and the current interest in their exploration, one must trace their history and the reasons for missions dedicated to them. Phobos and Deimos were discovered in the late 19th century by American astronomer Asaph Hall. From their discovery, these satellites aroused curiosity. Unlike the massive and almost spherical Earth's moon, they display an irregular, slightly elongated shape and modest size. Their appearance evokes that of asteroids captured by Mars's gravity, a hypothesis justified by their appearance: rocky blocks covered with craters without any evident internal structure. Other research suggests that they may originate from a major impact on Mars, with debris forming these small bodies. In any case, they orbit at low distances from the Martian surface. Phobos, the largest, is about 6,000 kilometers or 3,728 miles away, a remarkable proximity. Deimos, smaller and more distant, orbits about 20,000 kilometers or 12,427 miles away. This proximity implies that materials ejected during meteoritic impacts on Mars can reach their altitude, falling back as dust or fragments, hence the scientific excitement around biosignature dust. When a significant impact throws Martian debris into space, these materials can contain minerals, pulverized fragments, or even molecules from ancient life forms. If these particles cross the orbit of Phobos or Deimos, some of them may settle on their surface, where they remain preserved. Indeed, the Martian atmosphere is very thin, insufficient to disperse this dust, and Mars almost no longer has a magnetic field to disturb their retention. Over millions of years, these moons thus accumulate several layers of dust originating from Mars. Scientists estimate that if life existed on the red planet, or if organic molecules indicative of biological activities were formed there, some of these traces could be preserved on Phobos and Deimos. For researchers, exploring these layers is like reading a page of Martian geological and biological history. Before considering sample collection, it is necessary to specify the nature of these satellites. Phobos is about 27 kilometers or 17 miles long, while Deimos, smaller, reaches about 15 kilometers or 9 miles. Phobos is also remarkable for its orbit so low that it rotates faster than Mars on itself. From the Martian surface, it would appear to rise in the west and set in the east, an unusual phenomenon. Its surface is marked by a prominent crater called Stickney, while Deimos presents smoother contours, covered by a layer of regolith. The internal composition of these moons remains uncertain. They could be coherent bodies or loose assemblies. This uncertainty complicates landings, as ground that is too soft could cause a probe to sink. The term biosignature often appears in the search for extraterrestrial life. It refers to any indication that could demonstrate the current or past presence of living organisms, fossil cells, specific molecules, chemical traces. On Phobos and Deimos, the potential presence of such signatures does not stem from local life, but from the fact that they may have trapped dust from a Mars that was once inhabited. Their interest is heightened by the relative ease of collecting samples there. Landing on Mars is a major challenge due to gravity, the dense atmosphere, and the risks associated with descent. On these moons, the low gravity makes landing, collecting materials, and departing easier without the need for a complex thermal shield. Collecting dust there thus seems like a simpler way to obtain Martian fragments. Among current projects, the MMX mission, Martian Moons Exploration, developed by JAXA, is particularly anticipated, with a launch planned in 2026. Its objective is to study Phobos, collect samples, and bring them back to Earth for analysis. This mission has a dual purpose: to understand the origin of Phobos and Deimos, whether as captured asteroids or debris from a Martian impact, and to assess the amount of Martian material stored on the surface. The mineralogical and geochemical analysis of samples will allow the dating of dust, the identification of carbon compounds, and perhaps the detection of complex organic molecules associated with life. The MMX mission targets Phobos for practical reasons. Larger and closer to Mars, it is more exposed to particles ejected from the red planet. Its size also offers a larger surface area for collecting materials. If this mission provides conclusive answers, a future project could study Deimos to compare the dust present on the two moons. A single mission will not suffice to answer all questions, but this one will pave the way for other targeted explorations. The MMX probe will insert itself into Martian orbit and then position itself near Phobos. A lander module will deposit a small device capable of collecting a few grams or a few ounces of regolith. These samples will be secured in a capsule, which the probe will bring back to Earth. Several years later, this capsule will traverse Earth's atmosphere protected by a shield to land in an isolated area, thus avoiding any contamination. Laboratory analysis, with very sophisticated instruments, will focus on isotopic composition, chemical structure, and the presence of organic compounds. The ultimate goal of Martian exploration remains the discovery of past or present life. For this, several approaches are necessary: on-site observations, gas detection, and above all, the analysis of returned samples. Phobos and Deimos offer a prime target, capable of delivering Martian fragments without the difficulties of a landing on Mars. If complex organic molecules are found there, it will revive debates on their origin, dating, and the risk of terrestrial contamination. Rigorous protocols are planned to ensure the reliability of results from collection to storage. The success of MMX will demonstrate that it is possible to collect and return samples from a body in Martian orbit. This technological advancement will pave the way for more ambitious missions, such as the return of core samples from Martian soil. The results will also guide the relevance of a future mission to Deimos to compare biologically interesting dust between the two satellites. If stable organic molecules are identified, it will reinforce the idea that the Martian system is a natural laboratory for prebiotic chemistry, or even potential life. Every space mission must overcome obstacles. For MMX, precise navigation in Mars and Phobos' complex gravitational field will be essential to avoid collisions or trajectory loss. Surface contact is also uncertain. The regolith could be too soft or too hard, requiring robust and adaptable sampling tools. Finally, the return to Earth will demand strict planetary protection measures to avoid any cross-contamination, maintaining maximum caution, even if the presence of biological agents on Phobos is unlikely. MMX marks a new milestone in the study of Martian moons. Whether or not it discovers biological relics, the mission will enrich the understanding of the Martian system, the post-impact accretion processes, and the capability of small bodies to retain precious dust. Laboratories will analyze mineral and isotopic compositions, as well as the presence of complex carbon structures. Astrobiologists will look for any trace of biological activity, such as amino acids. In the absence of biosignatures, this data will refine the knowledge of non-biological phenomena in the Martian environment and help better target other exploration sites. Phobos and Deimos, despite their apparent simplicity, hold significant scientific potential. These small satellites, often mentioned last, are now becoming major targets. The MMX mission, scheduled for the coming years, aims to unravel their mystery and bring back an authentic fragment of the Martian system. These samples could reveal Mars's chemical history or even fossil biosignatures. This endeavor illustrates the continuous nature of space science, where each advancement opens up new questions. Finding evidence of extraterrestrial life, even ancient and microscopic, remains one of the greatest scientific and philosophical quests. On this path, Phobos and Deimos play the role of discreet sentinels, guardians of dust laden with hope, captured since the origins of the Red Planet. We are on the verge of major scientific challenges for the upcoming decade, centered on the search for life, understanding atmospheric processes, and preparing for Mars sample return missions. In this chapter, dedicated to the major questions of the 2025-2035 period, we will explore several essential directions. The first point concerns methane, a gas likely to reveal crucial clues about Martian geology and possibly biology. The second concerns the Mars Sample Return Program, which could finally provide a verdict on the possible presence of microfossil biosignatures. Then, we will discuss the potential viability of organisms capable of feeding on specific chemicals under 7 meters or 23 feet of regolith, the layer of dust and small pebbles covering Mars's surface. Finally, we will conclude with the preparation of the ExoMars mission, embodied by the Rosalind Franklin rover, which aims to drill up to 2 meters or 7 feet deep, equipped notably with the MoMA spectrometer, designed to detect complex organic molecules. All in the hope of answering a question that has fascinated for centuries. Does Mars harbor, or has it ever harbored, traces of life? Let's start with methane. This gas is composed of 1 carbon atom and 4 hydrogen atoms. On Earth, its main sources are biological, resulting from the metabolic activities of microorganisms or certain natural processes like organic decomposition in marshy environments. In our atmosphere, it is quickly destroyed by chemical reactions involving oxygen or other compounds, limiting its lifespan. On Mars, the situation is more complex. For several years, various instruments on the ground and in orbit have attempted to assess its presence. Some have detected low concentrations, on the order of a few parts per billion, while others have observed nothing. This divergence has sparked intense scientific debate. Interest in these Martian variations stems from the fact that methane, if emitted sporadically, could come from geological reactions between liquid water, carbon dioxide, and iron-rich minerals in the subsurface. But it could also result from biological activity, such as the hypothetical metabolism of underground microorganisms. What intrigues scientists is the rapid disappearance of this gas. If its production is occasional, why do its concentrations drop in just a few days or weeks? Recent studies suggest phenomena of adsorption on dust or unknown chemical reactions involving sunlight and the thin atmosphere. Future observations planned between 2025 and 2035 aim for precise daily monitoring to identify a possible correlation between geological zones and methane peaks. Researchers hope to elucidate the origin and fate of this potential marker of subterranean, geothermal, or biological activity. The second key point, undoubtedly the most publicized, is the return of Martian samples, or Mars sample return. This project includes several missions aimed at bringing back to Earth the rocks and dust collected by the Perseverance rover. The main challenge lies in the ultra-detailed analysis of these materials using laboratory instruments that are far more advanced than those aboard the rover. Scientists have equipment capable of detecting organic matter, the crystalline structure of minerals, and the precise isotopic composition of carbon and other elements. The goal is to resolve the question of the existence of microfossils, or molecules, characteristic of life. For decades, Mars has been studied remotely or by automated spacecraft. However, no definitive proof of life has emerged. In the past, the detection of simple organic molecules in Martian meteorites sparked hope, but each interpretation remained ambiguous, as it is challenging to differentiate an abiotic process from a biological signal. That's why bringing these rocks back to Earth is crucial. It will allow in-depth, repeated, and evolving analyses until the potential emergence of a microfossil signature, like mineralized filaments or trapped organic structures. A positive result would revolutionize our view of habitability in the solar system. Next, the question of the possible viability of perchlorate-reducing life under 7 meters or 23 feet of regolith deserves particular attention. Perchlorates, compounds of chlorine and oxygen, have been detected in several locations on Mars. On Earth, certain bacteria use these compounds as an energy source in the absence of other resources through chemical respiration, thus releasing useful energy. The question is whether, shielded from radiation and in the presence of traces of moisture, microbial colonies could survive under these conditions. Several factors come into play: the availability of an energy source, here perchlorates, and the presence of water, even as brine, which is very salty water that remains liquid at low temperatures. Mars experiences extreme surface temperatures, but geothermal heat and stable pressure under several meters, over 23 feet, can create more hospitable niches. This 7-meter depth corresponds to a zone where cosmic radiation is significantly attenuated, allowing for the possible survival of cells while permitting limited gas exchange with the surface. Finally, let's discuss the ExoMars mission, particularly the Rosalind Franklin rover. This vehicle, developed by the European Space Agency in international collaboration, is designed to drill up to 2 meters or 7 feet deep, a technical feat. This drilling must overcome low gravity, abrasive dust, and the constraints of Martian solar cycles. At this depth, samples might be preserved from cosmic and ultraviolet radiation, offering a unique potential to detect ancient organic molecules or fossils. The scientific core of the rover is the MoMA spectrometer, intended to detect complex organic compounds. It analyzes samples by progressive heating, releasing volatile molecules, then performs precise chemical separation and identification. The discovery of long or structured molecules would reinforce the hypothesis of prebiotic chemistry or ancient biology. The mission also includes cameras to study the texture of rocks and mineralogical sensors, allowing the crossing of chemical and mineral data to verify result consistency. By the late 2020s and early 2030s, when these missions have transmitted most of their data, the scientific community hopes to provide clearer answers. Resolving the methane mystery will provide clues about potential subterranean life and the deep geological dynamics of Mars. The return of samples could be decisive. The discovery of microfossils would mark a historical revolution, while an absence of biological evidence will enrich our understanding of Martian chemistry and habitability, guiding future research. Investigations into perchlorate-reducing life could reveal clues about volcanic or sedimentary chemistry, or even rare biological traces, radically transforming our understanding of life in extreme environments. The possible survival of microbes in sheltered niches, sustained by unusual energy resources, would suggest a universe more conducive to life, with implications for other worlds, such as the icy moons of Jupiter or Saturn. As for Rosalind Franklin, it represents a crucial step in the exploration of the Martian subsurface. Its MoMA spectrometer will play an essential role in confirming or refuting the presence of complex organic molecules. Success will also depend on the robustness of the drilling, the preservation of samples, and the rover's mobility in a challenging Martian environment. Drilling at a relevant geological site, such as an ancient riverbed or delta, could reveal the organic composition, mineral hydration, and traces of past conditions more favorable to life. Thus, the period 2025 to 2035 promises to be decisive in confirming or refuting certain scenarios on the habitability of Mars and the past or hidden presence of life. The mystery of methane could be clarified through precise monitoring, while the return of samples could conclude decades of speculations on microfossils. Whatever the result, it will guide the future of interplanetary exploration. The potential discovery of organisms using perchlorates would be a powerful symbol of extreme life, reminiscent of the surprising environments colonized on Earth. If such life exists on Mars, even rudimentary, it would open new perspectives on the distribution of life in our solar system. Finally, Rosalind Franklin, with its drill and MoMA spectrometer, embodies one of the most ambitious projects for the search for Martian life. By reaching 2 meters or 7 feet under the surface, it offers the hope of finding organic signatures preserved from radiation. Thanks to strict sterilization protocols and instruments capable of differentiating geological compounds and biological traces, this mission could deliver clues that challenge our uniqueness in the universe.